What if there is far more to the universe than we can currently comprehend? What if we are only beginning to scratch the surface of an infinite, awe-inspiring mystery that stretches beyond the limits of our imagination? The beginning of everything, the cosmos, with all its wonders, the unseen forces like dark matter and dark energy remains largely obscured from our senses, yet science continues to reveal bits of truth. Still, we stand on the edge of discovery, and the road ahead is filled with questions that may take generations to answer. At the heart of this monumental journey is the quest to understand the origins of the universe itself. To attempt this, we must dive deep into the folds of time, into a place where scientific theories merge with our boundless curiosity and imagination. One of the most widely accepted ideas is the Big Bang theory, which proposes that the universe began from a singular, infinitely hot and dense point roughly 14 billion years ago. This event, unlike anything we can fully fathom, set off an explosion of unimaginable energy and expansion, causing space itself to stretch out in ways that continue to unfold before us today. The very fabric of the universe began to expand at an extraordinary rate, and this process of cosmic growth shows no sign of slowing. It is this expansion that gives rise to the cosmos we observe today, vast, intricate, and ever-changing. Before the Big Bang, the conventional concepts of time and space break down. Scientists who study this critical moment in history often find themselves grappling with questions that challenge the very foundation of our understanding. Some have proposed that the universe could have originated from a state of singularity, where the laws of physics, as we know them, simply cease to exist. In this mysterious realm, all matter, energy, and space were compressed into an infinitesimally small point. What, then, could have existed before this singularity? What forces might have been at play in those first moments of creation? In addition to this, another fascinating idea emerges in the form of the multiverse theory. According to this hypothesis, our universe could merely be one among an infinite number of universes, each with its own distinct properties, physical laws, and even different versions of reality. If this theory holds true, it fundamentally transforms our perception of existence itself, suggesting that what we see around us may be just a small fragment of a far more intricate and boundless reality. Such a concept forces us to reconsider the boundaries of our universe, pushing the limits of our imagination and understanding. Then there are the cyclical models, which suggest that the universe doesn't simply begin and end in a linear fashion, but instead undergoes endless cycles of birth, death, and rebirth. In this vision, what we perceive as the beginning of the universe, the Big Bang, could simply be one chapter in an eternal cosmic cycle. Each expansion is followed by a contraction, each death followed by another birth. If true, these cyclical models offer a vision of the universe that is in constant flux, forever repeating its grandiose narrative in an infinite loop. These theories, each intriguing, each radical, collide with one another, offering answers to some of the biggest questions in science, while simultaneously leaving many mysteries unsolved. Each one pulls us deeper into the cosmic void, offering tantalizing glimpses into the truth, but never quite providing all the answers. As we look to the stars and delve into the cosmos, we are not just exploring the origins of our universe, we are also inviting questions that go far beyond what we currently know about existence itself. One such theory that reshapes our understanding of the early universe is the concept of cosmic inflation. This revolutionary idea suggests that in the briefest moments following the Big Bang, the universe underwent an unprecedented period of rapid expansion, far outpacing the speed of light. Imagine, if you will, a balloon that inflates instantaneously from a tiny speck to a vast expanse. This is, in essence, how inflation reshapes our view of the universe's birth. It was not a slow, gradual process as once imagined, but a sudden, explosive stretch that quickly set the stage for everything that followed. The significance of inflation lies not just in the way it reshapes our view of the early universe, but in the way it solves long-standing puzzles that have confounded scientists for years. Before inflation was proposed, scientists struggled to explain why distant regions of the universe, despite being separated by vast stretches of space, seemed so similar to one another. How could different parts of the cosmos share such uniform characteristics, such as temperature and density? Inflation offers an elegant solution. In the earliest moments of the universe, these regions were once in close proximity, allowing them to equalize before drifting apart. This sudden expansion not only allowed the universe to become more homogeneous, but also gave rise to the larger structures we see today, from galaxies to galaxy clusters. But the implications of inflation extend far beyond just explaining the uniformity of the universe. It provides insight into the origin of the vast cosmic web, the intricate arrangement of galaxies and clusters that stretch across the observable universe. The fluctuations in density during the inflationary epoch acted as seeds, small and subtle changes in the fabric of the universe that grew over time into the grand structures that now dominate the cosmos. However, as with every theory that offers explanations, inflation also opens the door to new questions. One of the most provocative aspects of inflation is its suggestion that our universe may not be the only one. In fact, inflation implies the existence of multiple universes, each with its own set of physical laws and properties, a concept that gives birth to the idea of the multiverse. This raises profound philosophical and existential questions about the nature of reality itself. Could we be just one tiny cog in a far larger, more complex machine? Could there be alternate versions of ourselves living in universes that are parallel to our own? As the concept of inflation continues to evolve, it not only helps to answer old questions, but also presents new mysteries. It asks us to reconsider our place in the cosmos and how we understand the very fabric of reality. The universe, it seems, is far more complex than we ever imagined. Of course, the Big Bang remains the most prominent theory explaining the origin of our universe. It marks a defining moment in history when all that we know, all that we experience, began as an incredibly hot, dense point. However, even though the Big Bang has become a cornerstone of modern cosmology, it is still shrouded in uncertainty, especially when it comes to the earliest moments of the event. At the moment of the Big Bang, the exact state of the universe remains one of the greatest mysteries. What exactly occurred during those first few moments when temperature and density were almost beyond comprehension? Scientists have established that the universe began to expand rapidly, but how this process unfolded and what triggered it is still not entirely understood. These moments, encapsulated within the theory of cosmic inflation, remain largely hypothetical, leaving many gaps in our knowledge. Equally mysterious is the formation of the fundamental forces and particles that shape the universe today. In the earliest moments after the Big Bang, the universe was a chaotic soup of energy. As it began to cool, particles started to form, transitioning from pure energy to matter. During this period, the forces that govern the universe, gravity, electromagnetism, and the strong and weak nuclear forces began to unify. How these forces acquired their distinct roles and how they came to govern the universe in the way they do now is a question that remains at the forefront of modern physics. What exactly happened in those early moments to shape the universe into the structured, yet ever-evolving entity it is today is still an enigma, waiting to be uncovered. As we look deeper into the origins of the cosmos, we are not just peering into the past, we are also staring into a future filled with uncharted territory and boundless possibilities. The universe remains a vast, mysterious expanse, full of hidden forces and untold secrets, and with every discovery, we find ourselves asking even more questions. What lies beyond the edge of our understanding? What mysteries remain just out of reach, waiting to be revealed? Only time will tell, but for now, the adventure of uncovering the truths of the universe continues to unfold before us, inviting us into the great unknown. The period immediately following the Big Bang, known as the radiation era, remains a somewhat elusive chapter in our understanding of the universe's early evolution. This phase, marked by rapid expansion, resulted in significant cooling, which eventually facilitated the formation of light elements such as hydrogen and helium. These building blocks of matter were produced when protons and neutrons fused together in a process known as primordial nucleosynthesis. Yet, the exact mechanics behind this nucleosynthesis continue to puzzle scientists, as the specific conditions and interactions that govern the formation of these elements are still under investigation. The abundance of hydrogen and helium in the universe provides tantalizing evidence of a delicate, finely tuned balance of forces and conditions present in the infant universe. However, despite numerous advances in cosmology, the full picture of how these elements came to be remains only partially understood. Moreover, dark matter and dark energy add profound layers of complexity to this already intricate narrative. These mysterious substances, which make up most of the universe's mass energy content, remain fundamentally invisible to us because they do not interact with light in any detectable way. While their existence is inferred from their gravitational effects on visible matter, their exact nature and origin continue to defy explanation. Dark matter, believed to exert gravitational influence on galaxies and clusters, and dark energy, thought to drive the accelerated expansion of the universe, both contribute to the cosmic puzzle. Together, they form a major challenge to our understanding of the cosmos, presenting questions that extend far beyond the observable universe into the very essence of existence itself. Adding another layer of insight, the cosmic microwave background radiation, the afterglow of the Big Bang, offers us a rare glimpse into the universe's infancy. This faint radiation, which dates back to a time when the universe had cooled enough for light to travel freely, serves as a cosmic fingerprint of the early universe. By studying this radiation, scientists have been able to glean essential information about the state of the universe just moments after its birth. However, despite the wealth of data it provides, the cosmic microwave background continues to reveal new mysteries. It holds critical clues about the uniformity of the universe, with some shedding light on how the seemingly chaotic and turbulent early universe evolved into the structured cosmos we observe today. The Big Bang theory, while offering a compelling framework for understanding the universe's origins, is far from complete. It presents a picture of cosmic beginnings that is still filled with unanswered questions. Each element of this grand narrative, from cosmic inflation and the formation of fundamental forces to the nature of dark matter and the remnants of the cosmic microwave background, poses significant challenges to our current understanding. These enigmas inspire continued research, with cosmologists constantly refining and revising their theories in an effort to uncover the deeper truths of the universe's inception. The remarkable uniformity of the universe, despite its chaotic beginnings, is one such mystery that scientists strive to explain. It is a curious phenomenon. How can a universe that emerged from a violent explosion be so orderly and consistent on such a grand scale? This puzzle has led to the development of the theory of cosmic inflation. Imagine for a moment the universe as a balloon in its infancy, small and nascent, yet poised for dramatic change. During this early phase, the universe underwent an extraordinary period of rapid expansion, growing faster than the speed of light. This inflationary period had profound consequences. It smoothed out irregularities in the distribution of matter and energy, creating a remarkably homogeneous cosmos. This rapid expansion stretched any initial temperature and density fluctuations caused by quantum variations across vast distances, effectively eliminating any large-scale irregularities. As the universe continued to expand, the remnants of these tiny imperfections remained, but they became statistical fluctuations rather than obvious, visible anomalies. These subtle variations laid the groundwork for the formation of structures like galaxies and clusters as gravity began to pull matter together. Over billions of years, these structures coalesced, creating the vast cosmic architecture we see today. In the vast scale of the universe, local environments may seem chaotic, but on a larger scale, patterns begin to emerge. These patterns, from the formation of galaxies to the clustering of galaxies, reflect the smooth, homogeneous state that existed in the universe's infancy. Gravity, alongside the laws of thermodynamics, plays a crucial role in this process. Gravity acts as a cosmic sculptor, pulling matter together and creating the vast structures we observe, while thermodynamics governs how energy is distributed across the universe. Together, these fundamental forces foster an intricate balance, allowing the universe to evolve from chaos to the elegant order we see in the galaxies, stars, and planets that populate the cosmos. Before the Big Bang, the very notion of existence as we understand it is shrouded in profound mystery. Most scientific theories suggest that the fabric of space and time, as well as the laws of physics, were not yet formed in any recognizable way. Imagine a state of absolute nothingness, where even the concepts of time, distance, and matter simply did not apply. This concept is difficult to imagine, as our experiences are deeply rooted in a universe that is filled with these very elements. Yet understanding this primordial state is crucial if we are to unravel the fundamental nature of reality itself. The importance of exploring the conditions before the Big Bang lies in its potential to answer some of the most profound questions in science and philosophy. How did the universe emerge from a state of nothingness? What caused the transition from an unfathomable primeval state to the universe we see today? The very idea that something could arise from nothing challenges our basic understanding of cause and effect and pushes the boundaries of both physics and metaphysics. Research into this early period often delves into the realms of quantum mechanics and the fundamental forces of nature. Some theories propose that fluctuations in a quantum field, an invisible field that permeates all of space, could have sparked the Big Bang. According to this idea, tiny, nearly imperceptible fluctuations in the quantum field might have triggered the massive, explosive expansion that followed, setting the stage for the universe to unfold as we know it. These theories stretch our understanding of what is possible, inviting us to reconsider the very foundations of reality and the origin of everything we perceive. Exploring the conditions that preceded the Big Bang offers us more than just a glance into the origins of our universe. It opens the door to fascinating realms that could radically reshape our understanding of existence itself. By delving into these enigmatic states, we can forge connections with concepts as far-reaching as black holes and the potential existence of multiple universes. These investigations do more than illuminate the past. They spark profound curiosity about other possible realms of existence, which in turn might dramatically alter our perception of reality. Through the lens of pre-Big Bang conditions, we confront some of the most fundamental questions about time, existence, and everything that exists within that vast spectrum, fueling humanity's unyielding quest for knowledge. Dark matter stands as one of the greatest unsolved mysteries in the universe. This elusive substance neither emits, absorbs, nor reflects light, rendering it invisible to our telescopes and impervious to our senses. Yet, despite its hidden nature, scientists have gathered compelling evidence that suggests dark matter makes up a substantial portion of the total matter in the universe. To understand its role, imagine the universe as an immense cosmic tapestry. The visible stars and galaxies, though dazzling, are just highlights woven into a far broader fabric, a fabric that remains largely unseen. This unseen material, known as dark matter, exerts a gravitational force that shapes the motion of galaxies and clusters of galaxies in ways that defy simple explanation. What makes dark matter so puzzling is its inability to interact with electromagnetic forces, the very forces that govern how light and radiation behave. In other words, it doesn't interact with light in a way that would allow us to directly observe it. We can see the movement of galaxies and the motion of galaxy clusters, but the amount of visible matter alone cannot account for these movements. This is where dark matter reveals itself, not through visible signals, but through its gravitational influence. It's akin to watching a grand dance performance where the dancers appear to move in perfect synchrony, yet an unseen force guides their steps. In the search for dark matter, scientists have employed a variety of techniques to capture its elusive presence. One method involves using underground experiments designed to detect rare interactions between dark matter particles and ordinary matter. These detectors are extraordinarily sensitive, capable of registering minute interactions that occur when a dark matter particle collides with an atomic nucleus. Though these events are extremely rare, each potential detection brings us closer to unlocking the secrets of this mysterious substance. Despite these efforts, dark matter remains stubbornly out of reach, largely because the particles we study on a regular basis do not seem to account for its existence. This ongoing uncertainty drives continued research as theorists explore possible candidates for dark matter particles, many of which may only interact through gravity, further complicating the search. The role of dark matter in the universe is far from academic. It is deeply intertwined with the very structure and formation of galaxies. If we think of a galaxy as a large celestial scale, the visible matter, comprising stars, gas, and dust, is but a fraction of the mass that actually exists. Dark matter, though invisible, acts as an unseen scaffold holding everything together. It plays a central role as galaxies form and grow, exerting its gravitational pull on surrounding mass, influencing the structure of the universe at the grandest scales. Without dark matter, galaxies would lack the gravitational force required to remain intact, leading to instability and potential disintegration. In essence, dark matter serves as the unseen glue that holds the cosmos together. One of the most striking manifestations of dark matter's influence is the rotation of galaxies. When we observe a galaxy, we expect its outer regions, farthest from the center, to rotate more slowly than the inner regions, in line with classical physics. Yet, in reality, galaxies exhibit an unexpected behavior. The outer stars and gas rotate at similar speeds to those near the center, implying the presence of much more mass than what we can observe. This anomaly can only be explained by the existence of dark matter, which exerts a gravitational pull on the galaxy, skewing the way the stars and other matter move. The influence of dark matter extends beyond individual galaxies and reaches into the realm of galaxy collisions. When two galaxies collide, the gravitational interaction between them is affected by the presence of dark matter. This invisible substance helps channel and guide the merger, influencing the resulting structure and the evolution of the new galaxy that emerges. Without dark matter, the universe would look radically different. Galaxies might fail to form, collide, or evolve in the same way, forever altering the cosmic landscape. Dark energy, too, is among the most profound mysteries of modern cosmology. It is thought to make up a significant portion of the universe's total energy content, more than both ordinary matter and dark matter combined. But its exact nature and properties remain elusive. Dark energy is responsible for the accelerated expansion of the universe, a phenomenon that is at odds with our conventional understanding of gravity. Rather than attracting objects together, dark energy pushes them apart, causing galaxies to move away from each other at increasing speeds. This strange force, counterintuitive to the forces we observe in our everyday experience, challenges the very foundations of physics. Unlike dark matter, which interacts through gravity, dark energy does not interact with any of the known forces, making it impossible to detect directly. Its effects are most evident on cosmic scales over vast distances and immense timeframes, which complicates efforts to study and understand it. Numerous theories have been proposed to explain dark energy, ranging from the idea that it is a property inherent to space itself to more speculative notions that involve modifications to our understanding of gravity. Each theory offers a different perspective on the universe, but none have yet provided a definitive answer, leaving dark energy as one of the most captivating subjects in cosmological research. The search for answers about dark energy goes hand in hand with questions about the ultimate fate of the universe. Will the universe continue to expand forever, driven by the force of dark energy? Or is there a limit to this expansion, a cosmic endpoint beyond which the universe can no longer stretch? These questions form the backbone of much of current cosmological inquiry, with each discovery inching us closer to understanding the true nature of dark energy and its implications for the future of the cosmos. Detecting and studying dark matter is one of the greatest challenges faced by modern astrophysics. Although scientists have yet to directly observe this mysterious substance, they are employing increasingly sophisticated methods to uncover its secrets. One such method involves the use of large underground detectors designed to capture rare interactions between dark matter particles and normal matter. These detectors are extremely sensitive, capable of registering tiny flashes of light or electrical signals produced when a dark matter particle collides with an atomic nucleus. The hope is that by identifying these rare occurrences, researchers can learn more about the nature of dark matter and perhaps even identify the particles responsible for it. Another approach to understanding dark matter involves studying galaxies and galaxy clusters. By observing the movements of galaxies and the way their stars and gas behave, scientists can infer the presence of dark matter. The faster than expected rotation of stars and galaxies, for example, reveals that there is more mass present than what we can account for with visible matter alone. By analyzing the motion of these celestial objects, astronomers can begin to map out the distribution of dark matter within galaxies, shedding light on its role in shaping the universe. Ultimately, the search for dark matter and dark energy is a journey into the unknown, a journey that promises to unlock secrets of the cosmos, challenge our most fundamental assumptions about the universe, and perhaps even reshape the way we think about existence itself. Furthermore, scientists are deeply investigating the potential for creating dark matter particles through high-energy particle collisions. In some of the largest and most advanced particle accelerators, like those at CERN, particles are smashed together at incomprehensibly high speeds. This creates conditions where researchers can probe the very fundamental building blocks of matter. Within this controlled environment, some researchers are optimistic that they might be able to produce dark matter particles, direct, tangible evidence of their existence. This effort represents a groundbreaking approach in the ongoing search to reveal the nature of the unseen force that shapes the cosmos. Meanwhile, astrophysicists turn their attention to the cosmic microwave background radiation, an ancient afterglow from the Big Bang itself. By studying tiny fluctuations within this radiation, scientists can piece together clues about the early universe. Specifically, they gain insight into how dark matter might have played a role in the formation of cosmic structures such as galaxies and clusters of galaxies in the early stages of the universe's evolution. This method adds another layer to the broader narrative of our cosmos, helping us to understand where dark matter fits into the grand scheme of things. As researchers strive to unravel the mysteries of dark matter, they employ a variety of methods to form a comprehensive approach. Each new discovery inches scientists closer to understanding the elusive and mysterious nature of this invisible substance that plays a crucial role in shaping the universe as we know it. In essence, every step taken is part of a broader and more exciting quest, one that might eventually reveal the unseen forces guiding the very fabric of our reality. Dark energy, another profound mystery, has captured the attention of modern astrophysicists. Traditionally, the force of gravity, as outlined by Newton and later expanded by Einstein, was understood as a force that attracts objects towards one another. It was widely believed that gravity's influence would gradually slow the expansion of the universe over time, pulling galaxies closer together. Yet, to the astonishment of scientists, observational data reveals a startling fact. Not only is the universe expanding, but that expansion is accelerating. This unexpected discovery has led to the introduction of dark energy, a force seemingly acting against gravity, pushing the universe apart at an ever-quickening pace. To grasp the concept of dark energy, imagine inflating a balloon. As air fills the balloon, it expands, much like the universe itself. Now, if gravity were the only force at play, we would expect the air inside the balloon to push inward, slowing its expansion. Instead, dark energy seems to act like an invisible hand, forcing the balloon to stretch even faster. This paradox lies at the heart of one of the most perplexing challenges in modern physics, understanding what dark energy actually is. Despite making up about 68% of the universe's total energy content, its interaction with matter is still poorly understood. A century ago, Einstein proposed the idea of the cosmological constant to explain a static universe. However, when it was discovered that the universe was expanding, he discarded the idea. Ironically, the concept of a cosmological constant may now hold a key to understanding dark energy, as it suggests a steady energy density that fills space evenly, pushing everything apart at a constant rate. This idea may explain the accelerated expansion of the universe. But as scientists dive deeper into this mystery, they face profound implications that challenge our current understanding of gravity and its role in the cosmos. Dark energy's existence forces us to reconsider our assumptions about gravity and the overall structure of the universe. It implies that our theories of how forces interact on both large and small scales are incomplete. This realization pushes the boundaries of physics, opening up new areas of theoretical speculation. In particular, it raises questions about the very fabric of space and time, suggesting that we may be on the verge of uncovering entirely new aspects of reality. The ongoing quest to understand dark energy could revolutionize our understanding of the cosmos and alter the trajectory of physics in profound ways. The formation of black holes, too, remains one of the most fascinating and enigmatic subjects in modern astrophysics. To comprehend how black holes come into being, we must first understand the life cycle of massive stars. When these stars burn through their nuclear fuel, they lose the ability to counterbalance the immense gravitational forces pulling inward. This often results in a catastrophic collapse. However, the exact mechanics behind this process continue to raise important questions. One of the most intriguing aspects is determining what factors dictate whether a star ends its life as a black hole or as a neutron star. Neutron stars represent a different form of matter, formed when a massive star undergoes a supernova explosion, yet retains enough pressure to prevent further collapse into a singularity. The boundary between these two outcomes, the creation of a black hole versus a neutron star, remains a point of contention. Scientists are investigating what role mass, rotation, and other factors play in determining the final state of a star. These questions lead to a broader mystery. How do stellar mergers factor into the formation of black holes? In environments where stars are in close proximity and orbit one another, their collision and subsequent merger could lead to the creation of black holes. Yet, the intricacies of how these mergers occur, along with the details of the resulting black holes, such as their mass, spin, and other characteristics, remain poorly understood. The study of these cosmic events promises to unveil new secrets about the universe and the nature of black holes. As we continue to probe these enigmatic phenomena, we are reminded that the universe is full of mysteries waiting to be uncovered. The answers, once found, could reshape our understanding of space, time, and the fundamental forces that govern the cosmos. Furthermore, the presence of supermassive black holes at the centers of galaxies introduces a multitude of additional questions, leaving scientists and astrophysicists alike grappling with some of the universe's most profound mysteries. These colossal entities, which are millions to billions of times more massive than our Sun, remain enigmatic, their origins still debated and actively researched. How do such enormous black holes form in the early universe, a time when conditions were vastly different from today? Did they gradually grow through the merging of smaller black holes and the accumulation of gas and matter? Or is there an entirely different pathway that allowed them to reach such mind-boggling sizes at the dawn of cosmic history? The mechanisms that underpin the formation of these supermassive objects remain a critical focal point for scientific investigation. In addition, there is the persistent enigma of dark matter, a mysterious and invisible substance that exerts an undeniable influence on the structure and behavior of the universe. How exactly does dark matter interact with supermassive black holes, if at all? Could there be a relationship between these elusive entities and the dark matter that permeates space, shaping the cosmic web? Unraveling these questions could not only help us better understand the role of black holes in the grand scheme of the cosmos, but also reveal new insights into the universe's most fundamental components. Every new discovery regarding black holes not only expands our knowledge of these strange and captivating objects, but also deepens our understanding of the broader forces that govern the universe itself. Black holes are, without a doubt, among the most fascinating and perplexing phenomena in the universe, primarily due to their extraordinary ability to warp both space and time. To grasp this concept, imagine space as a vast, flexible sheet. When an object with mass, such as a planet or a star, rests on this sheet, it creates a dent, akin to a shallow depression. The greater the mass of the object, the deeper the depression. However, when a black hole forms, typically through the collapse of a massive star, the resulting distortion in space-time is far more extreme. This is not just a small crease or dip in the fabric of space, but a profound and deep well that alters the way objects move through space and the manner in which time flows. As an object approaches a black hole, it encounters tremendous gravitational forces. This is where the warping of time becomes truly fascinating. Imagine watching a clock placed near the event horizon of a black hole. To an observer far from the black hole, this clock would appear to tick more slowly the closer it gets to the black hole's event horizon. This slowing of time is a direct result of the intense warping of both space and time due to the black hole's gravity, a phenomenon first predicted by Albert Einstein's theory of relativity. The stronger the gravitational pull, the more dramatic this effect becomes. While an individual near the black hole might experience time in a relatively normal manner, an outside observer would witness the passage of time stretching out as if it were being distorted by the black hole's immense gravitational field. This warping of space and time is not merely a theoretical curiosity. It holds profound implications for our understanding of the universe. The way black holes influence the passage of time and the structure of space aids scientists in grappling with fundamental questions about the nature of reality, the behavior of gravity, and the very fabric of the cosmos. It also ties into our broader understanding of the life cycles of stars, the formation of galaxies, and even the tantalizing possibility of time travel. As researchers continue to study black holes, each new discovery provides crucial insights that push the boundaries of our knowledge and help us uncover some of the most profound mysteries of existence. These discoveries reveal, with increasing clarity, just how interconnected everything in the universe truly is. At their core, black holes represent regions of space where the gravitational pull is so incredibly strong that nothing, not even light, can escape. As scientists delve deeper into understanding what occurs inside these mysterious cosmic giants, a variety of competing theories begin to emerge, each proposing different mechanisms that could explain the strange behavior of matter near or within black holes. One of the prevailing ideas suggests that once matter crosses the event horizon, the boundary beyond which no information can escape, it enters a realm governed by extreme gravity, where classical physics begins to break down. At this point, some theorists propose that matter is crushed into a singularity, a point of infinite density at the black hole's core, where the laws of physics, as we understand them, cease to function. This notion, however, raises several fundamental questions. If a singularity exists at the center of a black hole, what happens to it in relation to the rest of the universe? How does it interact with the cosmic fabric outside the black hole? This is where the principles of quantum mechanics come into play. Some scientists theorize that quantum effects might prevent the formation of a singularity altogether. Rather than collapsing into a single point, matter might create a new state of existence, or even serve as a bridge to another universe. Another possibility is that information about the infalling matter is not lost but imprinted on the surface of the black hole at the event horizon, a concept known as information preservation. There is also the tantalizing idea that space-time itself might behave differently within a black hole. Some models suggest that inside a black hole, space-time could be so warped that time operates in a fundamentally different manner than we experience in our own universe. The implications of this are staggering. Could traveling through a black hole allow one to journey into other dimensions or parallel universes, as some hypotheses suggest? What would the nature of reality itself look like if the boundaries of space and time were not as fixed as they appear to be? Moreover, the study of gravitational waves, ripples in space-time caused by massive events such as the merger of black holes, could offer further clues about what occurs inside these cosmic objects and the very fabric of reality itself. The ultimate truth about the inner workings of black holes may still lie beyond our current understanding, but each new discovery brings us closer to unraveling the secrets of these cosmic enigmas. Every breakthrough in the study of black holes, whether through theoretical models or observational data, contributes to our ever-expanding understanding of the universe and its fundamental nature. The mysteries of black holes are deeply intertwined with the principles of quantum mechanics and the fabric of space-time itself, and solving these puzzles could change our view of the cosmos in ways that are currently unimaginable. The relationship between black holes and quantum mechanics has long been a source of fascination and perplexity. When a star collapses under the weight of its own gravity, it forms a black hole, a region of space where gravity is so intense that nothing, not even light, can escape. This seems to present a paradox in the context of quantum mechanics, which hinges on the idea that information cannot simply vanish. Yet, according to traditional understanding, anything that falls into a black hole is lost forever, a contradiction to the principle of information conservation that lies at the heart of quantum theory. This information paradox has plagued physicists for decades, and many different theories have been proposed to resolve it. One of the most intriguing ideas comes from physicist Stephen Hawking, who proposed that black holes might emit radiation, now known as Hawking radiation, which causes them to gradually lose mass and eventually evaporate. If this process is real, it raises an important question. Does the information that falls into a black hole get lost forever when the black hole eventually evaporates, or is it somehow preserved and released as the black hole shrinks? Some physicists believe that the information might be encoded at the black hole's event horizon, the boundary beyond which nothing can escape, allowing it to be recovered at some later time, possibly in a form that is radically different from its original state. The interaction between black holes and quantum mechanics remains a rich and dynamic area of research, with new discoveries frequently challenging established ideas. These investigations delve into the very fabric of space-time itself, suggesting that our current understanding of gravity, time, and information is still incomplete. As both astrophysics and quantum mechanics continue to advance, the relationship between these two fields will likely provide crucial insights into the fundamental nature of reality, pushing the boundaries of our knowledge, and perhaps even reshaping our understanding of the universe itself. In addition to these theoretical considerations, black holes also play a critical role in the evolution of galaxies. At the centers of many galaxies, particularly the larger ones, lie supermassive black holes, their masses ranging from millions to billions of times that of our Sun. These gargantuan objects have a profound impact on the surrounding galactic environment in several ways. As matter spirals inward toward a black hole, it forms an accretion disk, a rotating disk of gas and dust that heats up due to intense friction and gravitational forces. This process can release immense amounts of energy, some of which is radiated away as electromagnetic radiation. The energy output from these accretion disks can either stimulate the creation of new stars or conversely suppress star formation by blowing away gas and dust that would otherwise coalesce into new stars. The influence of supermassive black holes extends beyond the accretion disk. Their immense gravitational pull affects the orbits of stars, gas, and dust in their vicinity, creating a dynamic environment. In some cases, the gravitational forces at play can lead to the merging of smaller galaxies into larger ones. As these galaxies collide, their central black holes may eventually merge as well, forming even larger black holes in the process. This merging of galaxies, driven in part by the gravitational interactions between their central black holes, plays a significant role in the growth and evolution of galaxies over cosmic timescales. The interconnectedness of black holes with the broader universe is clear. From their influence on time and space to their role in shaping the growth and structure of galaxies, black holes are fundamental to our understanding of the cosmos. As we continue to explore their mysteries, we move closer to understanding not only these enigmatic giants, but also the very nature of the universe itself. Moreover, black holes play a pivotal role in the dynamics of galaxies through the powerful jets they produce. These jets are ejected at nearly the speed of light when black holes consume surrounding material, and their effects ripple through space. As the black hole devours matter, it ejects a fraction of that material in the form of intense jets, stretching far beyond the immediate vicinity of the black hole. These jets have the capacity to influence surrounding gas clouds, pushing and pulling material in ways that directly affect star formation. In turn, they shape the structure of the galaxy, altering the way stars are born and how they evolve. Black holes are far from being passive, dormant entities in the universe. They are active participants in the intricate dance of galactic evolution. They are key players in shaping the interactions between galaxies, driving their growth, and influencing the very stars that populate them. The immense energy released by black holes and the subsequent disruption caused by their jets is a driving force in the complex dynamics of our universe. Neutron stars, on the other hand, represent one of the most extreme states of matter in the cosmos. These stellar remnants form when massive stars have exhausted their nuclear fuel and collapse under their own gravity. The result is a dense, compact object that challenges our understanding of the physical universe. Imagine compressing the mass of our sun into a sphere the size of a city. This is the density of a neutron star. A single teaspoon of neutron star material would weigh as much as an entire mountain on Earth. This immense density is what sets neutron stars apart from other celestial objects. What makes them even more extraordinary is their composition. They are primarily made up of neutrons. Neutrons are subatomic particles that, alongside protons, form the nucleus of atoms. In a neutron star, the gravitational forces are so intense that they compress protons and electrons together, creating neutrons. This results in a unique state of matter known as neutronium. Neutronium is so dense that it warps spacetime itself, creating an incredibly strong gravitational pull. Additionally, many neutron stars are observed as pulsars, rapidly rotating stars that emit beams of radiation as they spin. These beams sweep across space in a manner akin to a lighthouse beacon, casting light on vast stretches of the cosmos. The speed at which pulsars rotate is truly remarkable. Some spin hundreds of times per second, generating intense electromagnetic fields. This regular, pulsating behavior allows astronomers to study the properties of these stellar objects in detail, offering insights into some of the fundamental principles of physics and the nature of the universe. Pulsars serve as natural laboratories for understanding matter under extreme conditions, allowing scientists to probe the very fabric of space, time, and energy. The study of pulsars challenges our understanding of both quantum mechanics and general relativity, offering a window into the deepest mysteries of the universe. Within this fascinating category of neutron stars, magnetars represent an even more extreme subclass. These celestial objects possess magnetic fields that are about 1,000 times stronger than those found in ordinary neutron stars. To comprehend the behavior of these cosmic oddities, scientists employ a combination of advanced observational techniques and theoretical models. By examining the electromagnetic spectrum, especially in the X-ray and gamma-ray ranges, astronomers can peer into the inner workings of magnetars. These types of radiation are capable of penetrating even the densest materials, offering clues about the energy and magnetic fields of these extraordinary stars. The bursts of radiation emitted by magnetars allow scientists to infer crucial details about their magnetic fields. The energy and frequency of these emissions provide essential information about the strength of the magnetic field and its interactions with the surrounding material. The study of these emissions helps researchers gain insight into how the extreme magnetic forces at play within magnetars affect their surroundings. To capture this fleeting radiation, telescopes equipped with advanced detectors are used both on Earth and in space. By combining data from multiple observatories, researchers can track the magnetar's behavior in real time, creating a more comprehensive understanding of these intense objects. The magnetic fields of magnetars also have a profound impact on how these stars spin. By closely studying changes in the rotation rate, scientists can gain deeper insights into the internal structure of the magnetar. Through a combination of direct observations and complex mathematical models, astronomers are piecing together the mysteries of these enigmatic objects. Even though scientists cannot physically travel to magnetars, the integration of data from numerous sources allows them to continue unraveling the fundamental physics at play within these extreme environments. Each new discovery brings us closer to understanding the profound effects magnetars have on the universe, from their electromagnetic emissions to their impact on the surrounding space. Pulsars, another class of neutron stars, are among the most captivating objects in the cosmos. These highly magnetized, rapidly rotating stars emit beams of electromagnetic radiation from their magnetic poles. As these beams rotate, they sweep through space like the beam of a lighthouse, casting light on vast distances. If Earth happens to lie in the path of this beam, we observe regular pulses of radiation, each one occurring with incredible precision. Some pulsars exhibit such regularity that their pulses tick like the hands of a clock, offering an extraordinary tool for scientists studying the extreme conditions present in these objects. A pulsar forms when a massive star, having exhausted its nuclear fuel, can no longer support itself against gravitational collapse. As the core of the star implodes, the outer layers are blasted away in a violent supernova explosion, leaving behind a dense core. This core is so compact that a sugar cube-sized amount of pulsar material would weigh as much as the combined mass of all humans on Earth. As this remnant spins rapidly due to the conservation of angular momentum, its intense magnetic field generates the pulsar's signature emissions. The rate at which a pulsar spins can tell us a great deal about its mass, age, and the processes that occurred during its formation. Studying pulsars offers a rare and valuable glimpse into the conditions of matter under extreme stress and gravitational forces, shedding light on the complex processes that govern the universe. The regularity of pulsar emissions holds profound secrets about the universe. Each pulse a signal not only from the distant past, but also from the very fabric of space and time itself. These pulses, rhythmic and precise, can offer a wealth of information, shedding light on the environment that surrounds these enigmatic objects. The timing and nature of each emission are not arbitrary. They are shaped by the very matter that exists nearby. In fact, nearby matter can subtly influence the characteristics and timing of these pulses, acting like a cosmic fingerprint revealing the presence of otherwise invisible objects or forces. What makes pulsars even more fascinating is their ability to serve as cosmic laboratories, offering us a unique opportunity to test some of the most fundamental theories of gravity, such as Einstein's theory of general relativity. The precision with which pulsars emit their signals allows researchers to study how gravitational fields, both weak and strong, affect the passage of time and the behavior of light itself. This allows us to probe the very nature of the universe's underlying structure in ways that were once thought impossible. Each discovery made through the study of pulsars not only enriches our understanding of stellar evolution, but also brings us one step closer to unraveling the mysteries of the universe at its most fundamental level. Pulsars, in this sense, are far more than the remnants of dead stars. They are invaluable tools that help us decipher the life cycle of stars, both living and dying, across the cosmos. The very existence of these neutron stars challenges the limits of our knowledge and comprehension of astrophysics. These stars, formed from the remnants of once massive stellar bodies, represent one of the most extreme and fascinating phenomena in the universe. Born from the collapse of a massive star that has exhausted its nuclear fuel and exploded in a supernova, neutron stars are born from a process that sees the core of a dead star shrink under immense gravitational pressure. This collapse results in a state where protons and electrons are forced together, creating neutrons and thus giving rise to an object of extraordinary density. To put this into perspective, a single cubic centimeter of neutron star material would weigh as much as a mountain on Earth. This incredible density forces us to reconsider our entire understanding of matter. On our planet, matter is governed by the electromagnetic force, which keeps atoms and molecules stable. However, in the extreme conditions of a neutron star, gravity dominates. The electromagnetic forces that typically govern the behavior of matter on Earth are no longer significant in the presence of such intense gravitational forces. This leads to exotic forms of matter that we cannot replicate in laboratories on Earth, challenging not just our understanding of physics, but also our very definitions of what constitutes matter. Neutron stars, largely composed of neutrons, the building blocks of atomic nuclei, present an opportunity for scientists to probe the deepest mysteries of nuclear physics. The nature of matter at such extreme densities is still largely unknown, with some theories proposing that these stars could harbor exotic forms of matter. For example, hyperons, which are strange particles made of quarks, or even quark-gluon plasma, where quarks exist freely rather than confined within particles like protons and neutrons, could exist at the core of neutron stars. The mere possibility of these strange and exotic forms of matter pushes the boundaries of our understanding of the fundamental forces at play in the universe. To gain insights into the properties of neutron stars, scientists look to observations of their electromagnetic emissions and, more recently, their gravitational waves. The study of gravitational waves, ripples in space-time created by massive objects like neutron stars, has opened up a new way to probe these extreme cosmic objects. One of the most groundbreaking areas of research has been the study of neutron star mergers. When two neutron stars collide, the event produces a cataclysmic explosion known as a kilonova, which generates immense amounts of energy and results in the creation of heavy elements such as gold and platinum. These mergers have provided astronomers with a direct way to observe how some of the universe's heaviest elements are formed, adding an entirely new dimension to our understanding of the life cycle of matter. The detection of gravitational waves caused by these collisions has dramatically transformed astrophysics. In 2017, astronomers observed for the first time the ripples in spacetime caused by two neutron stars colliding, a discovery that validated a long-standing theory and revealed an entirely new avenue for observing the universe. This groundbreaking discovery also highlighted the ability to combine gravitational wave data with traditional electromagnetic signals, like light, to create a multisensory platform for studying cosmic events. Through this combined approach, scientists have gained new insights into the nature of gravity, the formation of heavy elements, and the very structure of spacetime itself. These observations represent just the beginning of a revolution in our understanding of the universe, promising to yield even greater revelations about the most powerful and enigmatic processes in nature. As we peer deeper into these cosmic events, we begin to understand not just the forces at work during these collisions, but also the larger structure of the universe and the origins of the elements that make up everything around us. The idea of additional dimensions beyond the familiar 3 dimensions of space and 1 dimension of time has long fascinated both scientists and the public. This concept is particularly explored in the framework of string theory, which suggests that the fundamental building blocks of the universe are not point-like particles as we once thought, but tiny vibrating strings. These strings are believed to oscillate in a variety of ways, but in order for the full range of their behavior to exist, extra dimensions beyond the 4 dimensions we experience are required. According to string theory, there may be 6 or 7 additional dimensions hidden from our perception and curled up so tightly that they are almost impossible to detect. This idea is one of the most intriguing aspects of theoretical physics, as it suggests that there may be far more to the universe than we can directly observe. A related theory that has captured attention is brain-world cosmology, which arises from string theory as well. In this view, our observable universe is not a flat, isolated entity, but rather a 3-dimensional surface, or brain, floating within a higher dimensional space. Events occurring in these extra dimensions may influence the physical laws and phenomena we experience in our own universe, even if we cannot directly observe these additional dimensions. The implications of these ideas are profound, suggesting that the universe we see around us may be part of a much larger, more complex structure that we are only beginning to understand. As we continue to explore the fundamental nature of reality, the discoveries we make about neutron stars, gravitational waves, and the very structure of space and time could ultimately lead us to a deeper understanding of the true nature of the universe and our place within it. In theoretical physics, the exploration of dimensions beyond the familiar 3 spatial dimensions is an avenue that has captivated scientists for decades. Central to many of these inquiries are quantum gravity models, which aim to bridge the gap between the seemingly incompatible realms of quantum mechanics and general relativity. These models explore the implications of additional dimensions, suggesting that gravity, when viewed in a higher dimensional context, might behave in ways that defy our conventional understanding. For instance, in a universe with more than the familiar 4 dimensions, 3 of space and 1 of time, the fundamental forces that govern our reality might interact in ways we have yet to imagine, revealing a cosmos far more intricate than we currently perceive. The idea of extra dimensions is not merely a speculative concept, but an active area of research. String theory, one of the leading frameworks in modern physics, posits that the universe might consist of not just the 3 spatial dimensions we experience every day, but many more, hidden from our senses, curled up in ways that escape detection at macroscopic scales. These additional dimensions could fundamentally alter how gravity and other fundamental forces operate. Picture, for instance, the world we know with its familiar length, width, and height. Now imagine that there are more dimensions compacted into spaces so small that they are undetectable to us. These extra dimensions are hypothesized to be compactified, meaning that they are tightly curled up far beyond our ability to observe directly. This notion of hidden dimensions has profound implications. Gravity, the weakest of the fundamental forces, could be dispersing into these extra dimensions, making it appear weaker in our three-dimensional world than it would otherwise be. If gravity is able to stretch out into these additional dimensions, it could provide a potential explanation for why, in comparison to forces like electromagnetism, it seems so feeble. Beyond gravity, the presence of extra dimensions could give rise to new particles and potentially modify our understanding of dark matter and dark energy, two of the most mysterious components of the universe, which are not yet fully explained by conventional theories. Moreover, extra dimensions could reshape our understanding of the early universe, particularly in the moments following the Big Bang. The extreme conditions of that time might have involved interactions that played out differently depending on the number of dimensions at play. These early cosmic events could, in theory, have been governed by rules that do not align with the laws of physics as we understand them today. The exploration of hidden dimensions, then, becomes more than just an academic exercise. It is an attempt to uncover the very nature of existence itself, to push the boundaries of perception, and to reveal a universe far more complex than our everyday experiences suggest. As scientists venture deeper into this uncharted territory, new theories are emerging to expand our view of the cosmos. Some cosmological models propose that our universe might be just one of many existing in a higher dimensional space, a bubble, if you will, among countless others. Each of these bubbles, or branes as they are sometimes called, could have distinct physical laws and constants. The possibility that our universe is only one of an infinite number, each with its own set of rules governing reality, has the potential to fundamentally alter how we perceive existence. This idea hints at a reality that is far grander and more diverse than anything we can currently comprehend. In the quest to prove the existence of these extra dimensions, scientists are employing a variety of innovative approaches. Particle colliders, such as the Large Hadron Collider, LHC, serve as one of the most promising tools in this exploration. In these high-energy experiments, protons are accelerated to nearly the speed of light and smashed together in an effort to uncover fundamental particles and forces. If extra dimensions exist, the energy released in these collisions could manifest as tiny black holes or other unusual particles, phenomena that might point to the presence of hidden dimensions. Detecting these events would provide a groundbreaking confirmation of higher dimensional space, offering a direct link between theoretical predictions and observable phenomena. Another avenue of research involves the detection of gravitational waves, ripples in space-time caused by the acceleration of massive objects, such as black holes or neutron stars. These waves carry information about the objects that produce them, and by studying their properties, scientists hope to uncover evidence of extra dimensions. If the laws of gravity behave differently in a higher dimensional universe, these alterations might be detectable in the way gravitational waves propagate through space. By identifying anomalies in these waves, researchers could gain crucial insights into the underlying structure of the universe. In addition, cosmic rays, which are high-energy particles from outer space, interact with Earth's atmosphere and produce showers of secondary particles. By studying these interactions, scientists hope to identify subtle deviations from expected patterns that could hint at the presence of extra dimensions. Such indirect evidence, while challenging to detect, could provide additional support for the idea that the universe extends beyond the familiar three dimensions. The potential for extra dimensions to reshape our understanding of reality is especially pronounced in string theory, which serves as a leading framework in the search for a unified theory of everything. String theory suggests that the fundamental building blocks of the universe are not point-like particles, but rather tiny, vibrating strings. The different ways in which these strings vibrate correspond to the different particles that we observe, much like the strings of a musical instrument producing different notes. These strings exist in a higher dimensional space, and their properties, including their mass, charge, and interaction with other particles, are influenced by how they move through the extra dimensions. Extra dimensions also play a crucial role in reconciling gravity with the other fundamental forces. In our four-dimensional understanding of space and time, 3 spatial dimensions and 1 temporal dimension, gravity behaves in a manner distinct from other forces, such as electromagnetism. By incorporating extra dimensions into the framework of string theory, scientists hope to bring gravity into harmony with the other forces, potentially providing answers to questions that current theories struggle to address. These questions include the behavior of black holes, the nature of dark energy, and the conditions that existed in the early universe. In this context, the study of extra dimensions is not just about pushing the boundaries of theoretical physics, it is an effort to understand the very structure of reality itself. By venturing into realms that lie beyond our familiar three-dimensional world, scientists are opening up new possibilities for what the universe might be, and how the forces that govern it could behave in ways we have yet to fully comprehend. As we continue to explore the depths of space and time, it is becoming increasingly clear that our universe is far more complex and mysterious than we can possibly imagine, and that the answers to the deepest questions of existence may lie in dimensions far beyond our reach. Extra dimensions have long fascinated scientists, providing a potential key to understanding why our universe appears to be so finely tuned. These hidden dimensions may hold the answers to some of the most profound questions about the constants of nature, such as why certain values like the strength of gravity are what they are. If we peer beyond the well-known 3 dimensions of space and time, we might uncover a deeper structure woven into the fabric of reality itself. String theory, for example, suggests that the universe is far more intricate than our everyday experiences suggest, offering a flexible framework to explore the mysteries of the cosmos. Traditionally, we experience reality in 3 spatial dimensions: length, width, and height, all anchored by the passage of time. Yet, theoretical models propose that there might be more, additional dimensions, intricately curled up and hidden from our perception. Imagine our universe as a 2-dimensional sheet of paper, simple and flat. If extra dimensions exist, they might be like folds or wrinkles in that paper, hidden from view, yet influencing everything that unfolds in our universe. These extra dimensions could be compacted so small that they remain unnoticed in our everyday lives. Or they might act as hidden pathways, connecting distant regions of space in ways that we are only beginning to imagine. Such extra dimensions could provide profound insights into some of the universe's most puzzling phenomena. For example, gravity is widely recognized as a weak force compared to the other fundamental forces of nature. However, if gravity were to spread out across these additional dimensions, it could explain its relative weakness in our 3-dimensional space. Perhaps, in the grander scale of the cosmos, gravity is not as weak as it appears. Its strength might be distributed across these extra dimensions, only seeming diminished within our limited perception of space. Moreover, extra dimensions could offer new avenues for understanding the fundamental forces and particles of nature. Particle physics, for instance, could be revolutionized if we were to discover how particles interact within these hidden dimensions. These interactions could give rise to novel forms of matter and energy, leading to new particles, forces, and even new laws of physics. The idea that these extra dimensions could be real shifts our perspective of the universe, pushing us closer to a unified theory that links gravity with the other forces of nature. In this new paradigm, the universe might reveal itself as far more complex and interconnected than our 3-dimensional reality suggests, beckoning us to explore its deepest secrets. One of the most tantalizing aspects of this concept is the possibility that these extra dimensions could illuminate some of the deepest cosmic mysteries. For example, how do the fundamental forces relate to one another in a higher dimensional space? How might the properties of gravity change when viewed through the lens of these hidden dimensions? As we continue to probe the nature of reality, the potential existence of extra dimensions could hold the key to answering these and other questions, revealing a universe that is more nuanced and mysterious than we ever imagined. At the other end of the spectrum, cosmic rays, high-energy particles that travel through space, offer another avenue for exploring the mysteries of the universe. These particles, which include protons and heavier atomic nuclei, are like messengers sent from the farthest reaches of space. They travel across vast distances, providing valuable information about the nature of the universe and the events that shape it. Some of these cosmic rays come from our own sun, while others seem to originate from faraway supernova, gamma-ray bursts, or even the enigmatic regions surrounding supermassive black holes. These high-energy particles are constantly bombarding Earth, and when they interact with our atmosphere, they produce secondary particles that scientists can detect and study. This process gives us a unique opportunity to learn about cosmic phenomena that are otherwise inaccessible. By examining the energy spectra of cosmic rays, scientists can infer the physical conditions of their sources, which may include the extreme environments of black holes or the aftermath of star explosions. Cosmic rays offer a glimpse into the heart of high-energy astrophysics, helping us understand the forces that shape the universe on the largest scales. In addition to their scientific significance, cosmic rays play a crucial role in space exploration. As they collide with Earth's atmosphere, they generate a shower of particles that can affect both the planet's environment and human technology. Cosmic radiation can interfere with satellite communications, damage electronics, and even pose a threat to astronauts venturing beyond Earth's protective atmosphere. Understanding how cosmic rays interact with the atmosphere is not only essential for understanding the universe, but also for protecting both space missions and the Earth itself. For future space exploration, designing effective shielding for spacecraft and spacesuits is crucial to ensure the health and safety of astronauts on long-duration missions, especially those traveling beyond Earth's orbit. The study of cosmic rays also helps to deepen our understanding of the universe's fundamental questions, such as the origins of matter and antimatter, as well as the dynamics of cosmic evolution. By analyzing the high-energy particles that travel across the universe, scientists are able to gain insights into the processes that shape the cosmos, from the formation of galaxies to the evolution of stars. These particles contain information about the history of the universe itself, offering clues about the fundamental nature of space, time, and the forces that govern them. In the pursuit of these mysteries, cosmic rays serve as both a window into high-energy astrophysics and a reminder of the vastness and complexity of the universe. Their presence is a constant, invisible reminder that the cosmos is a dynamic, ever-evolving entity. Whether they come from a distant supernova or the remnants of a black hole, cosmic rays are part of a broader cosmic dialogue that connects us to the farthest reaches of space. In studying these particles, we not only uncover the secrets of the universe, but also prepare ourselves for the challenges that lie ahead in the exploration of the unknown. Cosmic rays, high-energy particles traveling through the vastness of space, stand as one of the most enigmatic challenges in modern physics. These particles, originating from some of the most violent and extreme events in the cosmos, defy our conventional understanding of particle acceleration and propagation. Despite decades of research, the mechanisms behind how cosmic rays gain such immense energy remain an unsolved mystery, a puzzle that continues to intrigue and challenge scientists. This ongoing investigation is more than just a scientific pursuit. It holds profound implications for both space weather and the technologies that sustain life on Earth. The more we understand cosmic rays, the clearer it becomes that these particles are not merely travelers through space. They are cosmic messengers, offering insights into the very nature of the universe itself. The quest to comprehend cosmic rays extends beyond basic curiosity. It is critical for our understanding of the broad narratives that govern cosmic events, from stellar births and deaths to the very evolution of the universe. Each new discovery acts like peeling back a layer of the universe's complex fabric, revealing more about the forces at play, the mechanics behind cosmic phenomena, and the immense forces shaping existence. Cosmic rays, originating primarily from sources outside our solar system, such as exploding stars and the cataclysmic events of supernova, are the harbingers of deep space events. Upon their arrival at Earth, these particles don't just pass unnoticed. They interact with our atmosphere, creating a cascade of secondary particles and radiation. While Earth's atmosphere acts as a formidable shield, Absorbing and deflecting many of these incoming particles, some still manage to penetrate and reach the surface. Though the majority of these cosmic rays are filtered out by the atmosphere, their presence is not without consequence. Their interactions with the Earth's atmosphere result in secondary radiation that, while not posing a significant threat to human health under normal circumstances, can still have biological and ecological effects. These cosmic particles can interact with DNA, inducing mutations. Most of these mutations are harmless, even beneficial, but some can result in diseases, including cancer. Thankfully, the rate of such mutations remains relatively low, and the human body is equipped with remarkable DNA repair mechanisms that help mitigate the potential harm. The influence of cosmic rays is not limited to biology. In fact, their impact can ripple through the entire ecological system, indirectly affecting the environment, weather patterns, and even climate. One of the most fascinating effects of cosmic rays is their role in atmospheric chemistry, specifically in the formation of aerosols. These tiny particles serve as nuclei for cloud formation, and through their interaction with cosmic rays, they may play a significant role in climate regulation. Changes in cloud cover, which are influenced by the density of these aerosols, can affect temperature and precipitation patterns, thereby impacting weather on a global scale. Some researchers have even proposed the intriguing hypothesis that cosmic rays could influence life on Earth in more profound ways. These particles, they argue, might alter cloud cover, which in turn could have cascading effects on plant growth, animal migration, and even human behavior. While these ideas remain under investigation, they open up a broader conversation about the interconnectedness of cosmic events and life on our planet. Such findings suggest that the forces shaping the Earth and the forces shaping the cosmos are not as separate as once thought. Rather, they might be inextricably linked, with cosmic rays acting as a bridge between distant astronomical phenomena and the life processes on Earth. Among the most mysterious of all cosmic rays are those known as ultra-high energy cosmic rays. These particles, which include protons and atomic nuclei, possess energies far beyond anything achievable by human-made accelerators. These extreme particles provide scientists with rare and invaluable information about the most powerful events in the universe. Their origins remain elusive, though many believe they come from sources that are among the most violent in the cosmos. Supernova explosions, collisions of massive celestial bodies, or even the energetic centers of galaxies that house supermassive black holes. The very nature of these particles suggests that they are tied to some of the universe's most extraordinary phenomena. When these ultra-high energy cosmic rays reach Earth, they are not mere passengers. They carry with them traces of their origins and the processes that produced them. By studying their interactions with the Earth's atmosphere, physicists can reconstruct the violent cosmic events that gave birth to them. These cosmic rays, upon striking the atmosphere, create a cascade of secondary particles, which can be detected by ground-based observatories. These interactions provide a unique window into the nature of high-energy physics, allowing scientists to explore fundamental questions about the properties of matter, the forces that govern the universe, and the mechanics of cosmic evolution. Each ultra-high energy cosmic ray serves as a messenger from the furthest reaches of space, offering clues to some of the universe's deepest secrets. These particles are not just carriers of energy, they are pieces of cosmic history. By understanding them, scientists can gain insights into the most violent processes in the universe, from the formation of stars to the behavior of dark matter. Moreover, the study of these particles provides an opportunity to understand the role of magnetic fields in shaping their trajectory through space, shedding light on the fundamental forces that govern the cosmos. In essence, cosmic rays are not merely high-energy particles. They are fragments of the universe's most extreme events, providing a glimpse into the workings of the universe itself. They allow us to explore the dynamic processes that shape everything around us. When these cosmic rays interact with the Earth's atmosphere, they create a cascade of secondary particles that can be detected and analyzed. This process allows scientists to investigate the energy production mechanisms of stars, the composition of distant celestial bodies, and even the elusive nature of dark matter. Each cosmic ray, whether originating from a distant galaxy or the explosion of a supernova carries with it valuable information about the universe's past and present, shedding light on the forces and events that shape the cosmos. Cosmic rays offer us a rare and invaluable window into the extreme conditions of the universe, providing insights into environments that are otherwise beyond the reach of laboratory experimentation. These high-energy particles, which come from sources scattered across the cosmos, offer a unique perspective on the forces at work in places where ordinary physical conditions would crumble. As these particles travel through space and collide with the Earth's atmosphere, they reveal secrets about phenomena that we cannot replicate here on Earth, from supernovae to black holes. Their study allows us to deepen our understanding of the universe's most extreme and fundamental processes. Yet, cosmic rays are not only useful for exploring the distant reaches of the cosmos, they have practical implications here on Earth as well. As they bombard our planet, these particles can interfere with technological systems such as satellites, causing malfunctions and disruptions. Astronauts venturing into space are similarly vulnerable to the radiation carried by these cosmic rays, which can pose serious health risks during prolonged exposure. Thus, studying cosmic rays becomes not just an academic pursuit, but a necessary step to safeguard our technological infrastructure and human endeavors beyond Earth's protective atmosphere. By decoding the mysteries surrounding cosmic rays, we unlock crucial knowledge about the universe's past, its current state, and its potential future. Quantum mechanics adds yet another layer to our understanding of the cosmos, revealing a universe where the very fabric of reality seems to defy the rules that govern our everyday experiences. While classical physics allows us to predict the motion of large objects with a high degree of certainty, quantum mechanics operates on a different scale, one where uncertainty and probability reign supreme. At the subatomic level, particles like electrons do not have a fixed position or velocity until they are measured. Instead, they exist in a state of possibility, a blur of potential outcomes until observed. This concept is mirrored in the cosmos, where certain phenomena, such as the behavior of light and gravity, also appear to blur the boundaries of our conventional understanding. Light itself, for example, behaves both as a particle and as a wave, depending on how it is observed. This duality hints at deeper paradoxes embedded in the very nature of reality, where distinctions between seemingly separate states can become indistinct. One of the most intriguing intersections of quantum mechanics and cosmology occurs in the study of black holes. When matter is crushed into the incredibly dense singularity of a black hole, it creates an environment where the laws of quantum mechanics must be used alongside those of general relativity, which governs gravity and the curvature of space-time. This interplay gives rise to profound questions about the very nature of information, such as whether data that falls into a black hole is truly lost to the universe, or if it could exist in a sort of holographic format on the event horizon. Another fascinating aspect of quantum mechanics is the phenomenon of quantum entanglement, where particles become linked in such a way that the state of one particle instantly influences the state of another, regardless of the distance between them. It's as though two entangled dice could show the same number at the exact same time, no matter how far apart they are in space. This mysterious connection challenges our basic concepts of locality, the idea that objects only influence their immediate surroundings, and suggests that our universe might be far more interconnected than we currently understand. Could there be hidden dimensions or unknown forces allowing this instantaneous communication to occur? This possibility stretches our understanding of space, time, and causality in ways that we are just beginning to grasp. Quantum entanglement is not just a theoretical curiosity. It has practical applications with the potential to revolutionize fields like quantum computing and cryptography. By harnessing the principles of quantum mechanics, scientists hope to develop technologies that can process information in ways that classical computers could never achieve. Despite these advances, however, there are still deep mysteries surrounding quantum entanglement that remain unsolved. Why do certain particles become entangled in the first place? What role does the observer play in determining the state of these particles? As we continue to probe these questions, we may uncover answers that could fundamentally reshape our understanding of the very fabric of reality. This pursuit of knowledge leads us to reconsider how the universe itself may have emerged. In the aftermath of the Big Bang, the universe expanded rapidly during a period known as cosmic inflation. During this time, quantum fluctuations, tiny, random changes in the energy of empty space, could have laid the groundwork for the intricate structure of galaxies, stars, and other cosmic formations that we observe today. As we continue to integrate quantum mechanics with our cosmological models, it invites us to rethink the nature of reality itself and opens the door to new revelations that could change our perception of the cosmos forever. One of the most fascinating and perplexing aspects of quantum mechanics is its potential to help us understand the enigmatic nature of black holes. These colossal entities, defined by their immense gravitational pull, have long been shrouded in mystery. Not even light can escape their grasp, rendering them invisible to conventional observation. Yet, quantum mechanics provides a new lens through which we can explore their nature. The principle of uncertainty, for example, suggests that we cannot know both the position and momentum of a particle with absolute precision. Near a black hole, this uncertainty could give rise to strange phenomena like quantum fluctuations, where particles spontaneously appear and disappear, even in the extreme environment surrounding a black hole. This means that in the space near a black hole, matter and energy are never truly at rest. They are constantly fluctuating in a dynamic dance. Perhaps the most intriguing prediction arising from quantum mechanics is Stephen Hawking's theory of Hawking radiation. According to Hawking, black holes may not be entirely black after all. Instead, they could emit radiation due to quantum effects that occur near their event horizon. This process arises when particle-antiparticle pairs form just outside the event horizon. While one particle falls into the black hole, the other escapes, resulting in a small but measurable amount of radiation. Over incredibly long periods of time, this process could lead to the gradual evaporation of the black hole itself, challenging our traditional notions about these cosmic behemoths. As we continue to explore the quantum world, these ideas push us to think beyond the familiar laws of classical physics, suggesting that the universe is far more complex than we ever imagined. As we continue to probe the deepest mysteries of the cosmos, we are constantly reminded that the universe is a vast, interconnected web of phenomena, some we can observe, others that remain elusive. The study of cosmic rays, quantum mechanics, and black holes not only enriches our understanding of the universe, but also challenges our most fundamental assumptions about reality itself. With each new discovery, we edge closer to unraveling the enigmatic threads that weave the fabric of space and time, bringing us closer to understanding the true nature of existence. Furthermore, quantum mechanics not only reshapes our understanding of the microscopic world, but also sparks profound discussions about information in classical physics. In traditional views, anything that falls into a black hole is thought to be lost forever. However, quantum theory introduces a paradox, suggesting that information cannot be destroyed. This ongoing debate about the fate of information within a black hole is more than a theoretical curiosity. It could ultimately challenge and transform our entire understanding of reality. As scientists intertwine quantum mechanics with black hole physics, they are tackling some of the most fundamental mysteries of the cosmos, including the elusive relationship between gravity and the quantum forces that govern the smallest particles in the universe. Through this intersection of quantum theory and black hole dynamics, researchers are revealing new layers of complexity that challenge our existing conceptions of the universe. The deeper we explore, the more we begin to question what we think we know about the fabric of space-time and the fundamental laws that govern it. The more we peel back the layers, the clearer it becomes that the universe is far stranger, more intricate, and more interconnected than we could have ever imagined. It is as though the laws of physics themselves are evolving, challenging even the most deeply held assumptions about the nature of existence. As this research continues to unfold, it has the potential to reshape not just our scientific theories, but our very understanding of the cosmos. In the vast, seemingly empty expanse of space, the vacuum is far from empty. Instead, it teems with invisible, ephemeral entities known as virtual particles. These particles are born from the energy fluctuations that occur in the vacuum. According to quantum mechanics, energy and matter are not separate, they are interconnected. This allows for the spontaneous creation of particle-antiparticle pairs, which appear for a brief moment before annihilating one another. Think of virtual particles as fleeting guests at a cosmic party. They appear out of nowhere, perhaps exchanging energy, interacting with other particles, and exerting tiny but significant forces on the surrounding space before vanishing just as mysteriously as they arrived. Despite their transient existence, these virtual particles are far from inconsequential. They play a fundamental role in shaping the forces we observe in the universe, including gravity and electromagnetism. These brief interactions, though invisible to the naked eye, contribute to the forces that govern the behavior of real particles, even though they themselves are short-lived. Virtual particles also play a crucial role in processes such as Hawking radiation. Around black holes, when one of these particles escapes the immense gravitational pull, its partner falls into the event horizon. This process results in a gradual loss of mass by the black hole, demonstrating how, even in the emptiness of space, these seemingly inconsequential particles are woven into the very fabric of the universe, shaping everything from the behavior of light to the destiny of massive celestial bodies. The influence of virtual particles also reveals the remarkable dynamism of the vacuum. Far from being an inert void, the vacuum is an active, vibrating, ever-changing environment, filled with a constant flux of particles that subtly shape the very nature of the cosmos. This interconnectedness between virtual particles and the universe challenges the conventional view of empty space, urging us to rethink the fundamental qualities of the cosmos and its underlying mechanisms. Even in the emptiest regions where we might expect silence and stillness, the universe is far from still. It is a space of constant activity, pulsating with the energy of quantum interactions, each of which plays a role in the grand cosmic drama. At its core, quantum mechanics provides critical insights into the very origins of our universe. This branch of physics governs the behavior of the smallest particles, at scales so minuscule that the classical laws of physics no longer apply. In the quantum realm, the rules are radically different, and phenomena can seem utterly counterintuitive. One of the fundamental principles of quantum mechanics is uncertainty. Particles do not have definite positions or velocities until they are observed or measured, which means that in the quantum world, multiple possibilities can coexist simultaneously, each as valid as the next. This principle fundamentally challenges our classical ideas of determinism and introduces a new reality where probabilities and uncertainties reign. This quantum framework becomes especially crucial when considering the origins of the universe. The moment often referred to as the Big Bang marks the beginning of space and time as we understand it. But before this event, the universe existed in a state of extreme density and heat, governed entirely by quantum effects. During this primordial phase, fluctuations in energy could spontaneously occur, resulting in variations that may have eventually given birth to the universe in its present form. These fluctuations, arising from the uncertainty inherent in quantum mechanics, might have created small pockets of energy that rapidly expanded, giving rise to matter and radiation as the universe began to cool. The very fabric of the universe as we know it today may have emerged from this chaotic quantum-driven process, revealing that the universe's beginnings were not a simple orderly event but a turbulent phase shaped by quantum probabilities. Moreover, theories such as quantum inflation extend these ideas even further. They propose that in the moments immediately after the Big Bang, the universe experienced an explosive, rapid expansion, driven by quantum fluctuations in energy. This theory not only helps explain the observed uniformity of the cosmos, but also accounts for the large-scale structures we see today, such as galaxies and clusters. These quantum fluctuations during inflation might have set the stage for the formation of everything we observe in the universe, from the distribution of galaxies to the vast cosmic web that binds them together. The connection between quantum mechanics and cosmology, however, is still far from fully understood. As modern physics pushes the boundaries of both fields, it seeks to unravel the deepest mysteries of existence itself. By exploring the origins of the universe through the lens of quantum mechanics, we are forced to confront some of the most profound questions about reality. Could the universe have emerged from a quantum fluctuation? Is the true nature of reality at its core governed by probability and uncertainty? These questions invite us to reconsider not only the birth of the cosmos, but also our understanding of the very laws that shape our world. The process of galaxy formation and evolution continues to be one of the most captivating puzzles in astrophysics. To understand how galaxies came into existence, we must travel back to the early moments of the universe immediately following the Big Bang. In this newborn universe, a seething cauldron of hydrogen and helium filled the vastness of space. As the universe expanded and cooled, regions of gas began to condense under the influence of gravity, eventually leading to the formation of the first stars and galaxies. One of the central questions in galaxy formation is how these initial gas clouds, composed primarily of hydrogen, grew into the diverse and complex structures we observe today. Recent theories suggest that dark matter, a mysterious substance that cannot be seen directly but is known to exist because of its gravitational effects, may have played a crucial role in this process. Dark matter, despite being invisible to telescopes, is thought to have formed a kind of scaffolding in the early universe. Around this dark matter structure, visible matter began to clump together, eventually giving rise to galaxies. This dark matter scaffold could explain the observed distribution of galaxies, from spiral galaxies like our own Milky Way to elliptical and irregular galaxies. The gravitational influence of dark matter likely helped galaxies form within the deep gravitational wells it created, leading to the rich variety of shapes, sizes, and structures that populate the universe. In this way, the study of galaxy formation and evolution intertwines with the larger questions of cosmology, led from the origin of the universe itself to the enigmatic properties of dark matter. As we continue to explore the cosmos, we are uncovering a universe far more complex and interconnected than we ever anticipated, one where the smallest quantum fluctuations can shape the largest structures in the universe. Each discovery leads us closer to understanding not only how galaxies formed, but also how the fundamental forces of nature work together to shape the very fabric of the cosmos. Across the vastness of space, we are confronted with a profound set of questions that challenge our understanding of the universe. One of the most intriguing is the origin of the wide variety of galaxy types, ranging from the spirals we recognize to the more elliptical forms. What processes have shaped these galaxies over time, and how do they come to exhibit such diverse structures? An essential piece of the puzzle is the role played by the environment itself. How do factors such as density and the gravitational influence of nearby galaxies affect a galaxy's overall structure and evolution? Could interactions between galaxies, such as collisions, mergers, or close encounters, have a profound impact on how these galaxies evolve, not just structurally, but also in terms of star formation and internal dynamics? The importance of star formation cannot be overstated when it comes to galaxy evolution. The initial bursts of star creation within a galaxy can set the stage for its future. For some galaxies, star formation is an ongoing process, actively shaping their development and size. In contrast, other galaxies may have ceased star formation long ago, leaving behind an aging stellar population. This variation in star-forming activity raises critical questions about the underlying factors that dictate whether a galaxy remains active or enters a phase of dormancy. What is the role of supermassive black holes, which reside at the centers of most galaxies, in these processes? These colossal objects, with their immense gravitational pull, may not only shape the dynamics of their host galaxies, but could also influence the rate at which stars form or cease to form altogether. Their presence complicates our understanding, turning what might seem like simple phenomena into intricate interactions between gravity, matter, and energy. As we explore the fate of galaxies over billions of years, it becomes evident that galaxies are not static entities. Over time, galaxies interact in ways that often lead to dramatic transformations. Some galaxies merge, creating hybrid structures that combine features of their progenitors, while others undergo significant changes due to external forces such as the tidal effects of neighboring galaxies or internal processes like galactic winds. These interactions can trigger new waves of star formation, or conversely, they can suppress it entirely. In this sense, a galaxy's journey through the universe is as much about its relationships with its cosmic neighbors as it is about its own intrinsic development. One of the most fascinating mysteries in astrophysics revolves around the observation of galaxy rotation curves. When astronomers observe how galaxies rotate, they measure the speed at which stars and gas move around the galactic center at various distances. According to classical physics, and based on the visible mass of a galaxy, the rotation speed should decrease as one moves farther from the center, similar to how planets in our solar system move slower the farther they are from the sun. However, this is not what astronomers observe. In many galaxies, the rotation speeds remain constant or even increase as one moves farther from the center. This discrepancy suggests that there is more mass in these galaxies than can be accounted for by the visible matter alone. The solution to this puzzle has led scientists to propose the existence of dark matter, a mysterious substance that does not emit or absorb light, making it undetectable through traditional means. The concept of dark matter has fundamentally changed our understanding of the universe. It is thought to make up the majority of the mass in the universe, providing the extra gravitational pull necessary to explain the unexpected rotation speeds observed in galaxies. Despite decades of research, the true nature of dark matter remains elusive. It is possible that it consists of exotic particles yet to be discovered, hinting at new physics beyond the standard model. Some theories even suggest that instead of a new form of matter, we may need to reconsider our understanding of gravity itself. While dark matter remains hidden from view, its gravitational influence is apparent in the rotation of galaxies, the movement of galaxy clusters, and the large-scale structure of the universe itself. The search for dark matter is one of the most exciting frontiers of modern science, as it promises to unveil a deeper understanding of the forces that govern the cosmos. In addition to dark matter, there is another major mystery, the so-called missing matter within galaxies. While we can observe stars, gas, and dust within galaxies, calculations suggest that these visible components make up only a small fraction of a galaxy's total mass. The rest of the mass, we believe, is made up of dark matter, which does not interact with light or other forms of electromagnetic radiation. This invisible substance can be inferred from its gravitational effects, such as the fact that galaxies rotate faster than would be expected based on the visible matter alone. If only the visible matter existed, galaxies should fly apart due to the lack of sufficient gravitational pull. Yet they remain intact, suggesting the presence of an unseen force. Despite extensive efforts to detect dark matter directly, its true nature remains a mystery, and the question of what constitutes this missing matter continues to perplex scientists. Further complicating the issue is the realization that the distribution of matter within galaxies is not uniform. Observations of galaxy clusters and large-scale cosmic structures show patterns that defy current models. There are hints that this missing matter may be concentrated in regions that are difficult to observe, or that it may not be uniformly distributed at all. This raises additional questions about the nature of dark matter and its interaction with normal matter, as well as its potential role in the formation and evolution of galaxies. New technologies such as more powerful telescopes and advanced particle detectors are helping to push the boundaries of our knowledge, bringing us closer to understanding the true composition of the universe. One of the most fascinating aspects of galaxy evolution is the interaction between galaxies. Far from being isolated, galaxies are constantly moving through space and often come into close proximity to one another. When this happens, their gravitational fields interact in ways that can result in dramatic changes to their shapes and structures. For example, when two galaxies approach one another, their mutual gravity can stretch them into long tidal tails, streams of stars and gas that extend far beyond the original galaxy. In some cases, these interactions can even trigger bursts of star formation, creating new stars at rates far exceeding what is typical for an isolated galaxy. These starbursts can make galaxies temporarily more vibrant and active, leading to spectacular displays of brightness that can be observed across great distances. In some cases, galaxies will merge, combining their stars, gas, and dust to form a new, larger entity. These mergers can lead to the formation of hybrid structures that retain some characteristics of the original galaxies, but with entirely new features. Mergers can also trigger new waves of star formation, as the collision of gas clouds and the distortion of galactic shapes create the perfect conditions for the birth of new stars. However, these interactions can also have the opposite effect, quenching star formation entirely, as the disturbance strips away the necessary materials or disrupts the delicate balance required for star creation. The fate of galaxies is, therefore, not only a matter of their internal processes, but is deeply influenced by their cosmic neighbors, whose gravitational influence can shape their destiny in unexpected ways. In the grand scheme of things, the evolution of galaxies is a story of constant change and interaction. From the birth of stars to the merging of galaxies, the processes that shape these celestial structures are as dynamic and unpredictable as the universe itself. Each discovery in this field brings us closer to unraveling the mysteries of the cosmos, shedding light on the forces that have shaped and continue to shape the galaxies that populate the vast expanse of space. Galactic encounters with their intricate dynamics often give rise to outcomes that defy our current understanding of cosmic evolution. While some galaxies merge to form a unified entity, others pass by one another in a cosmic ballet, only to separate after the briefest of encounters. These interactions, though fleeting, leave lasting imprints, gravitational influences that can persist for millions of years, subtly altering the galaxy's motions. These lingering effects shape the galaxy's future trajectories, steering them into new paths that could never have been predicted. At the heart of these interactions lies an additional layer of complexity: dark matter. This elusive, invisible substance does not emit light or energy, making it almost impossible to detect directly. Yet its gravitational pull on stars and gas within galaxies is profound. This unseen force adds a layer of unpredictability to galaxy dynamics, influencing their movements and interactions in ways that visible matter alone cannot account for. As a result, the galaxy's orbits often take unexpected turns, with phenomena that challenge our deepest assumptions about cosmic behavior. The ever-changing interactions between galaxies serve as a constant reminder of the dynamic nature of our universe. They continuously reshape the cosmos in ways that broaden our understanding of the forces at play in the formation and evolution of galaxies. In this vast cosmic theater, scientists are perpetually on edge, constantly uncovering new insights that disrupt previous models and theories. A key to understanding these processes lies in the diverse shapes that galaxies assume as they evolve. When we look across the universe, we observe a breathtaking variety of galaxy structures. Some take the form of elegant spirals, their arms unfurling gracefully in space, while others present an irregular, almost chaotic appearance. These strange and distorted shapes often signal the tumultuous history of the galaxies, stories of collisions, mergers, and cosmic turmoil. Galaxies do not exist in isolation. They are part of an ever-evolving cosmic environment, deeply influenced by the gravitational forces of neighboring galaxies. When two galaxies collide, the gravitational tug-of-war between them can cause their forms to warp and stretch. This interplay of forces can stretch one galaxy into strange, elongated shapes or induce the formation of new stars in the areas where gas clouds collide. In these star-forming regions, vast clouds of gas are compressed, triggering a burst of new stellar creation that can light up the galaxy in a burst of brilliance. The event alters the very nature of the galaxies involved, both in appearance and in their ongoing evolutionary paths. This is not merely a visual transformation, but a profound shift in the very essence of the galaxy itself, one that can lead to the birth of entirely new stellar systems. Furthermore, galaxies can be influenced by processes known as tidal interactions. Imagine two large objects floating in a body of water. Each movement they make sends ripples that interfere with one another. Similarly, when galaxies come close to each other, their mutual gravitational attraction can bend and twist their structures, creating unusual shapes and phenomena. These interactions, like the ripples in water, are often subtle but have profound consequences. Over time, they reveal the history of the galaxy's encounters, with every curve and distortion offering clues about the nature of their relationship. Often, The more irregular shapes found in certain galaxies suggest that they are in a relatively young or active phase of their life cycle, possibly the result of recent mergers or external influences. As galaxies age, they undergo continuous changes, with their shapes evolving over billions of years. The intricate and unusual forms we see today are often the result of mergers, collisions, or the subtle but significant effects of dark matter. Dark matter, though invisible, exerts a tremendous gravitational influence on the cosmos, shaping the formation of galaxies and affecting their interactions. The distribution and presence of dark matter play a pivotal role in determining the paths that galaxies take as they evolve. These cosmic fingerprints, irregular shapes, and peculiar formations are not mere anomalies, but tell the story of the galaxy's past. They reveal the forces, events, and interactions that have shaped each galaxy, helping scientists piece together the complex narrative of the universe's history. In the search for extraterrestrial life, humanity embarks on one of the most ambitious and profound quests in history: the search for intelligent life beyond our planet. This endeavor, though steeped in scientific rigor, is also deeply personal, answering the question of whether we are truly alone in the universe or part of a larger cosmic community. Several strategies are employed in this search, each adding a piece to the puzzle of extraterrestrial existence. One of the primary methods is the use of radio telescopes to scan the heavens for unusual signals. The premise behind this approach is simple, yet profound. Advanced civilizations, much like our own, might use radio waves to communicate across vast distances. By monitoring the radio frequencies of the cosmos, scientists hope to detect repeating or unique signals that might indicate the presence of intelligent life. A complementary strategy to this radio search is the exploration of exoplanets. These are planets that orbit stars outside our solar system. By analyzing the data gathered from space telescopes, scientists can identify exoplanets that lie within the habitable zone of their stars, the region where conditions may be conducive to the presence of liquid water, an essential ingredient for life. The study of these exoplanets, particularly their atmospheres, reveals key insights into the potential for life. Gases like oxygen and methane, which are often associated with biological processes, can indicate that a planet might host life, offering a tantalizing clue that we are not alone in the cosmos. Another avenue of exploration is the active search for extraterrestrial intelligence, SETI. This strategy involves sending messages into space, broadcasting our existence, and hope for a response. Rather than waiting for a signal, humanity takes the bold step of reaching out, offering a cosmic invitation to any advanced civilizations that might be listening. It is a courageous and hopeful endeavor, like a step towards initiating a conversation with the unknown. Technological advancements in artificial intelligence, AI, have greatly enhanced our search efforts. AI tools can process vast amounts of data much more efficiently than human analysts, allowing researchers to identify patterns, signals, or anomalies that might suggest extraterrestrial activity. With these tools, the search for intelligent life has entered a new era, one where computational power works hand in hand with human curiosity and ingenuity. Additionally, the study of extremophiles, organisms that thrive in the most hostile environments on Earth, offers crucial insights into the kinds of life that might exist in extreme conditions on other planets. From deep-sea vents to boiling deserts, extremophiles have adapted to environments once thought inhospitable to life. This research expands our understanding of the diversity of life forms that might exist elsewhere, suggesting that life could exist in forms and under conditions previously considered impossible. These organisms redefine what it means to be habitable, and by studying their resilience, scientists refine their search for life beyond Earth. The probability of extraterrestrial life is calculated using a multifaceted approach that blends astronomy, biology, and statistics. One key tool in this effort is the Drake equation, which attempts to quantify the likelihood of extraterrestrial civilizations by considering variables such as the rate of star formation in our galaxy, the number of stars with planets, and the fraction of those planets that could support life. This equation provides a framework for estimating the number of potential civilizations in our galaxy, offering hope that we may not be alone in the vast expanse of the universe. Through the study of exoplanets, the discovery of planets in habitable zones, and the search for alien biosignatures, scientists have uncovered many promising signs. The ongoing search is a testament to humanity's insatiable curiosity and its desire to understand our place in the cosmos. The search for life beyond Earth is one of the most captivating and complex endeavors in modern science. As researchers delve deeper into this mystery, they explore a multitude of factors that could support life on other planets. The chemical makeup of a planet's atmosphere is one such crucial element. Scientists carefully scrutinize the presence of essential building blocks like carbon, oxygen, and nitrogen, which are fundamental to life as we know it. By analyzing data gathered from space missions and powerful telescopes, researchers build a clearer picture of these elements' distribution across distant worlds. This growing body of knowledge helps scientists assess whether these planets could host life, providing a valuable insight into the potential for life beyond Earth. As this investigation progresses, statistical models become instrumental. These models take all the accumulated data from various missions, telescopic observations, and previous discoveries to calculate the likelihood of life on other planets. By integrating information from a vast array of sources, scientists can estimate how often life might arise under different conditions across the cosmos. This ongoing synthesis of findings forms the backbone of humanity's search for life beyond our own world. The signals that reach us from deep space are full of scientific potential. From radio waves to light, these signals offer clues about the universe, from its formation to its vast complexities. One of the most intriguing phenomena under investigation are fast radio bursts, intense bursts of radio waves that release enormous amounts of energy in mere milliseconds. The energy released during a fast radio burst is comparable to the total output of our sun over an entire day. Yet, the origin of these bursts remains elusive. Some scientists suggest that they could be linked to violent cosmic events, like the collision of neutron stars, while others entertain the possibility that they might be signals from advanced extraterrestrial civilizations. This dual possibility, either as a natural cosmic occurrence or a signal from intelligent beings, adds layers of excitement and mystery to the search for life in the universe. Alongside these radio bursts, another cosmic puzzle involves cosmic background radiation. This faint afterglow of the Big Bang is the oldest light in the universe, offering a snapshot of the universe when it was just a fraction of its current age. Analyzing this radiation has provided critical insights into the formation of galaxies and the overall structure of the cosmos. However, the subtle variations within this radiation still spark ongoing questions, challenging scientists to deepen their understanding of its meaning and implications. Furthermore, the study of gravitational waves has opened an entirely new frontier. These ripples in the fabric of space-time are generated by massive celestial events, such as the collision of black holes or the merging of neutron stars. When these waves reach Earth, they carry with them a wealth of information about the events that created them. The detection of gravitational waves has allowed scientists to peer into the most extreme and energetic regions of the universe, offering profound insights into both the nature of the cosmos and the very structure of space-time itself. In addition to these natural phenomena, the concept of extraterrestrial signals has become a major focus for astronomers. Projects like the Search for Extraterrestrial Intelligence, SETI, aim to detect potential signals from intelligent alien civilizations. By carefully analyzing the vast noise of cosmic background radiation, scientists look for patterns or structured signals that could indicate the presence of advanced beings. Each detected signal, no matter how fleeting or ambiguous, sparks excitement and speculation, as it might be the breakthrough that forever alters our understanding of life beyond Earth. The flood of signals reaching our planet from the cosmos is far from random. They are more like whispers from the universe itself, carrying secrets about the origins and structure of our cosmic neighborhood. Every new discovery, no matter how small, draws us one step closer to answering some of humanity's oldest and most profound questions. Are we alone in the universe? These signals hold the potential to reveal not only the nature of distant worlds, but perhaps even their inhabitants. The discovery of alien life would mark a turning point in human history, a revelation that would forever reshape our understanding of existence itself. For centuries, we have wondered whether we are the only life forms in an unfathomably vast universe. The confirmation of life beyond Earth would provide profound validation to the idea that life is not a unique anomaly to our planet. It would suggest that the building blocks of life, perhaps simple molecules and essential elements, could combine in diverse environments across the universe, creating life in forms we have yet to imagine. Whether microbial or highly advanced, the discovery of alien life would challenge our understanding of biology, evolution, and the very conditions necessary for life to flourish. It's entirely possible that life on distant planets has adapted to environments radically different from our own, thriving in extreme conditions such as high radiation or extreme temperatures. Some life forms might even rely on entirely different chemical bases, defying everything we thought we knew about biology. Such revelations would expand our definition of life itself, breaking down barriers about what is essential for survival and forcing us to reconsider how life can exist. Beyond the scientific implications, the discovery of alien life would ignite a host of philosophical and ethical discussions. What would it mean for humanity's place in the universe? Could we communicate with these beings, or would cultural and biological differences create insurmountable barriers? The discovery could lead to discussions about cooperation, conflict, or the potential for sharing knowledge and resources across vast cosmic distances. Our assumptions about intelligence, social structures, and evolution would be challenged in ways we can't yet predict. The search for extraterrestrial life would undoubtedly ignite a renewed interest in space exploration, particularly in the study of astrobiology, the study of life in the universe. As we learn more about how life might exist in other parts of the cosmos, our space missions would become more focused. Researchers would target environments on distant planets or moons that could potentially harbor life, such as the icy surfaces of moons orbiting gas giants or the atmospheres of far-off exoplanets. The quest for alien life would transform from a distant hope into a focused global effort. Detecting signs of life on exoplanets, however, is not without its challenges. The vast distances between us and these planets make gathering light and data an inherently difficult task. Even when light from these distant worlds does reach us, it is often faint and buried beneath the overwhelming brightness of the stars they orbit. This distance alone presents a significant challenge, but the complexity of interpreting the signals adds another layer of difficulty. Biosignatures, indicators of life, can take many forms, such as specific gases in a planet's atmosphere. However, these gases can also be produced through non-biological processes. For example, methane could be a byproduct of geological activity, not necessarily linked to life. This means that scientists must rely on sophisticated analysis and intricate models to determine whether a gas is of biological origin. Only with precise methods can we differentiate between signs of life and the natural processes of the planet. Instrument limitations also present a significant hurdle. The telescopes and sensors used for this research must be incredibly sensitive to detect even the faintest biosignatures, the glare of distant stars. Developing instruments capable of achieving the necessary sensitivity and resolution to study exoplanet atmospheres is a formidable task. Additionally, the unique weather and atmospheric conditions on these distant planets may alter or obscure biosignatures before they ever reach our telescopes, further complicating the analysis. Despite these challenges, the search for alien life continues to drive scientists and researchers forward by pushing the boundaries of technology and knowledge. Each new discovery, every breakthrough, and every question raised brings humanity closer to answering one of the most profound questions of all. Are we truly alone in the universe? Understanding the spectrum of light that passes through alien atmospheres offers scientists an invaluable tool for inferring their compositions. However, this process is not as straightforward as it might seem. The methods required to decipher these spectra are extraordinarily complex, involving intricate models and delicate instruments to piece together information about distant worlds. In this endeavor, a significant challenge remains: confirming the presence of a biosignature. Even if an anomaly is detected in the light spectra, the data must be compelling enough to rule out the possibility of false positives. The search for life beyond Earth, as a result, becomes not just a quest for discovery, but an intricate puzzle that demands sophisticated technology, well-rounded theoretical models, and, most importantly, irrefutable data to confirm the existence of life elsewhere in the cosmos. Gamma-ray bursts are among the most captivating and mysterious phenomena observed in the universe. These intense, high-energy flashes of gamma rays represent the most energetic form of electromagnetic radiation known to science. When a gamma ray burst occurs, it releases an amount of energy that can surpass the energy emitted by the sun over its entire lifespan, all within just a few seconds. These bursts are so powerful that they often reach Earth from distances that span billions of light years, making them one of the most spectacular events in the universe. However, despite their incredible brightness and energy, the origins of gamma-ray bursts remain shrouded in mystery. Scientists have identified two primary causes for these bursts: the collapse of massive stars and the collision of neutron stars. In the first scenario, a massive star, having exhausted its nuclear fuel, succumbs to gravitational collapse, eventually forming a black hole. This collapse triggers a violent explosion, a gamma-ray burst. In the second scenario, two neutron stars, the remnants of collapsed stars, spiral toward one another. As they draw closer, their mutual gravitational pull causes them to merge in a catastrophic event, releasing an immense burst of energy. While researchers have a basic understanding of these two primary origins, many of the intricate details involved in these processes remain elusive. The variability of gamma-ray bursts only adds to the complexity of studying them. Some bursts last only a fraction of a second, while others can persist for several minutes. The intensity of these bursts can also fluctuate dramatically, further complicating efforts to study them. This variability and unpredictability present a significant challenge to astronomers who often must rely on detecting these bursts after they have already occurred. Since gamma-ray bursts are located billions of light years away, by the time their light reaches Earth, it has traveled through vast stretches of space and time. In this way, these bursts offer us a rare and invaluable opportunity to glimpse into the early universe, providing insight into the formation of stars, galaxies, and the evolution of cosmic structures over time. Each discovery surrounding gamma-ray bursts adds a piece to the puzzle, allowing researchers to deepen their understanding not just of these spectacular events, but also of the fundamental laws that govern the universe. These bursts, in their fleeting brilliance, reveal the complex interplay of forces that shape the cosmos. The discovery of fast radio bursts, FRBs, another mysterious astrophysical phenomenon, has further challenged existing models of the universe. Unlike gamma-ray bursts, which are characterized by intense flashes of gamma radiation, FRBs are incredibly brief but incredibly powerful bursts of radio waves. Their brevity, lasting only a few milliseconds, combined with their enormous energy output, which can equal the energy emitted by the sun over the course of several years, leaves researchers with little time for observation or detailed study. For years, scientists believed that cosmic radio signals like those emitted by pulsars or supernova could be neatly classified within established models of known astrophysical phenomena. Yet, fast radio bursts do not fit neatly into any of these categories, and their true origins remain elusive. The sheer intensity of these bursts, along with their enigmatic nature, has led scientists to entertain a variety of speculative theories. Some researchers suggest that these signals could emanate from exotic cosmic objects that have yet to be discovered, while others speculate that they might even be the result of advanced technological activity, possibly from extraterrestrial civilizations. The possibility that such bursts could be artificial in origin opens up a tantalizing realm of possibilities, forcing astrophysicists to re-examine their understanding of the universe. As the search for answers continues, each new observation of fast radio bursts offers more questions than answers, prompting researchers to broaden their scope and challenge the very foundation of astrophysical models. In both cases, gamma-ray bursts and fast radio bursts, researchers are not merely searching for the origins of these phenomena. They are also testing the limits of our current understanding of physics, probing the very nature of space, time, and the fundamental forces that govern the universe. Each discovery, no matter how incremental, acts as a stepping stone toward greater knowledge, revealing the underlying complexities of the cosmos and, perhaps, one day leading us to answers that could fundamentally alter our view of existence itself. The search for these answers is an ongoing journey, one that challenges our preconceived notions and opens up new realms of possibility for understanding the universe and our place within it. Fast radio bursts, FRBs, have emerged as one of the most enigmatic and puzzling phenomena in the universe, challenging our conventional understanding of astrophysics. These intense bursts of radio waves, often lasting just a few milliseconds, provoke profound questions about the mechanisms driving such extreme emissions and the environments from which they originate. Traditional models of galaxy evolution and cosmic energy dynamics struggle to explain the unique conditions that give rise to these bursts. The typical assumptions, based on the idea that matter and energy are distributed evenly throughout the cosmos, fail to account for the observed behaviors and characteristics of FRBs. Consequently, researchers are compelled to rethink their foundational theories, delving into uncharted territory to explore new models that can accommodate these bursts. This requires a radical shift in our understanding of the fundamental forces of the universe, such as gravity, radiation, and the behavior of matter under extreme conditions. Accepting that there are gaps in our knowledge compels the scientific community to embark on new lines of inquiry. The quest is not only to understand the bursts themselves, but also to examine the broader cosmic environments that host these enigmatic signals. Each new detection of a fast radio burst offers tantalizing clues, urging astronomers to refine their models and expand their theoretical frameworks. As a result, these fleeting phenomena serve as markers of the immense complexity woven into the fabric of the universe, forcing scientists to stretch the boundaries of their understanding. Fast radio bursts represent more than just a cosmic mystery. They are a critical challenge that pushes the limits of current astrophysical knowledge, beckoning the need for more comprehensive and dynamic models. Similarly, gamma-ray bursts, GRBs, one of the universe's most powerful and violent explosions, have captivated scientists for decades. These extraordinary events release vast amounts of energy, often exceeding what our sun could emit over its entire lifespan, all within a matter of seconds. The leading theories regarding GRBs suggest two primary scenarios. The first involves the collapse of massive stars. When these stars exhaust their nuclear fuel, they can undergo a supernova explosion, which may eventually lead to the formation of a black hole. During this collapse, the star may emit jets of energy traveling at nearly the speed of light, unleashing a torrent of gamma rays. These jets can be detected across immense distances, making them observable from Earth. The second theory suggests that GRBs are the result of neutron-star mergers, cataclysmic collisions between two of these ultra-dense remnants of supernovae. These collisions not only generate intense gravitational waves, but also release a burst of gamma rays, often accompanied by the formation of a black hole. Recent observations have brought new insights showing that not all GRBs are identical. Long-duration bursts, which can last from a few seconds to several minutes, are typically associated with the collapse of massive stars, while short-duration bursts, lasting only a few seconds, are linked to neutron-star mergers. This distinction has enabled scientists to refine their understanding of the phenomenon and piece together a more comprehensive model. As astronomers continue to improve their observational techniques and instruments, the exploration of GRBs continues to yield valuable insights into the life cycles of stars, the formation of black holes, and the underlying processes that govern cosmic evolution. When a gamma-ray burst occurs, it unleashes a torrent of energy, enough to surpass the sun's total output over its entire lifetime in mere seconds. These bursts create powerful jets of radiation and matter, expelled at velocities close to the speed of light. This extreme release of energy significantly alters the environment around the burst. As the energy radiates outward, it collides with surrounding gas and dust, generating shock waves. These shock waves heat the matter to millions of degrees, causing it to emit light across a spectrum of wavelengths, including X-rays and visible light. The force of the shock waves can compress nearby gas, triggering the formation of new stars. In this sense, gamma-ray bursts, though violent and destructive, are also capable of fostering the birth of new stars from the very chaos they create. The immediate effects are intense, but the long-term consequences of these bursts can be just as profound. The radiation released by a gamma-ray burst has the potential to strip away the atmospheres of nearby planets, or at the very least disrupt any existing ecosystems. The intense radiation can break molecular bonds, leading to chemical changes in the affected regions and potentially disrupting the development of life. In essence, the aftermath of a gamma-ray burst can dramatically alter the landscape of a planet, leaving it radically different from the way it was before. On a broader cosmic scale, the consequences of such explosions ripple across the universe. These events can enrich the interstellar medium, the space between stars, with heavy elements produced during the birth and death of massive stars. Over time, this process contributes to the overall chemical evolution of galaxies. In this way, gamma-ray bursts serve not only as a powerful force of destruction, but also as important catalysts for the creation and redistribution of the elements that make up the universe. The impact of gamma-ray bursts extends beyond their immediate surroundings. If such an event were to occur close to Earth, the effects could be catastrophic. The intense radiation could strip away the protective ozone layer, exposing life on Earth to harmful ultraviolet light. Without this vital shield, the surface of the planet would be subjected to radiation that could damage genetic material, disrupt cellular processes, and potentially lead to mass extinction events. In addition to the immediate thermal effects, gamma-ray bursts also unleash high-energy particles that travel at nearly the speed of light. If these particles collide with a planet's atmosphere, they can produce secondary radiation that might penetrate to the surface, further exacerbating the potential for catastrophic effects. For planets like Earth that harbor life, the consequences of such a burst could be devastating, causing rapid extinction events that might disrupt the evolutionary process. On a larger scale, the frequency of gamma-ray bursts in any given region of the universe could influence the likelihood of life developing there. Areas with frequent bursts of high-energy radiation may be less hospitable to life, as their destructive potential could prevent life from taking hold or flourishing. As a result, the search for habitable exoplanets becomes a more complex and nuanced endeavor. Astronomers must take into account not only factors like the distance from a star and the presence of liquid water, but also the frequency of catastrophic events, such as gamma-ray bursts that could wipe out any developing life. The potential for these bursts to disrupt the formation of life makes them a significant consideration for scientists studying the habitability of other worlds. Gamma-ray bursts, while awe-inspiring and captivating from a scientific perspective, also represent an existential threat to life as we know it. Their capacity to fundamentally alter planets and ecosystems raises important questions about the fragility of life in the universe. As astronomers continue to study these phenomena, they are not only deepening our understanding of the cosmos, but also learning more about the potential for life to emerge and survive within it. Meanwhile, cosmic voids, vast expanses of empty space, have begun to reveal important secrets about the universe's structure. These voids, which contain far fewer galaxies than the surrounding regions, are essentially the opposite of galaxy clusters, which are densely packed with stars and other celestial bodies. To identify a cosmic void, scientists look for regions where the density of matter, particularly galaxies, is significantly lower than average. These voids can span millions of light years across, appearing as massive gaps in the cosmic landscape. By studying large-scale surveys of galaxies, researchers can identify areas where the distribution of galaxies is sparse, using advanced statistical methods to quantify these voids and map their extent. Despite their emptiness, cosmic voids play a vital role in our understanding of the universe. They provide critical insights into the large-scale distribution of matter and the forces that have shaped the cosmos since the Big Bang. By studying these voids, scientists can gain a better understanding of dark energy and dark matter, two of the most mysterious and influential forces in the universe. These invisible components of the cosmos drive the expansion of the universe and play a key role in the formation of its large-scale structures. Far from being mere emptiness, cosmic voids are integral to unraveling the mysteries of the universe, offering clues about the nature of dark energy, dark matter, and the overall evolution of the cosmos. At the heart of our cosmic understanding lies the question of what the universe is made of. While ordinary matter, the kind that makes up stars, planets, and living beings, is well understood, scientists have encountered a perplexing phenomenon, the existence of missing baryonic mass. Observations of the cosmic microwave background radiation, the faint glow left over from the Big Bang, suggest that there should be more visible baryonic matter than we can currently detect with our instruments. In theory, if all of the baryonic matter assumed to exist were accounted for, there should be more observable matter in galaxies and clusters than we currently observe. One possible explanation for this missing mass is that much of it exists in forms that are difficult for us to detect. Baryonic matter can exist as cold, diffused gas, so thinly spread across vast regions of space that it does not emit or reflect light. This elusive form of matter may reside in the vast cosmic filaments that stretch between galaxies, where its density is too low to be detected by current telescopes. The search for this missing baryonic mass continues, driving forward our understanding of the universe's composition and structure. Some scientists speculate that parts of the missing baryonic matter could be concealed in the atmospheres of distant exoplanets or even in small, faint stellar objects that lack the necessary luminosity to be easily detected. Another fascinating theory posits that primordial black holes, which might have formed in the universe's earliest moments, could account for a portion of the unaccounted mass. This remains an open question, and it is not merely an academic pursuit. In fact, the implications of uncovering the truth about this missing mass stretch far beyond curiosity. It could dramatically reshape our understanding of galaxy formation, the evolution of the universe, and even the fundamental laws of physics. As our observational techniques become more refined and technology continues to advance, we move ever closer to unlocking the secrets of this elusive baryonic matter. With each step, we inch toward not only understanding the structure of the cosmos, but also probing the very fabric of reality itself. Cosmic voids, those vast, seemingly empty regions scattered across the universe, play an essential role in shaping the large-scale structure of the cosmos. Picture the universe as a vast honeycomb, where the dense sections represent galaxies and clusters of galaxies, and the empty spaces between them correspond to the voids. These enormous vacuums are not simply empty expanses, but powerful regions that profoundly influence the behavior of cosmic matter. The gravitational forces of denser regions pull matter toward them, creating a unique dynamic around cosmic voids. These voids act almost like gravitational traps. Matter from the surrounding denser areas is drawn toward the void's peripheries, leaving the central regions even emptier. Over time, this process leads to the expansion of the voids as galaxies and clusters move toward the denser regions. The influence of cosmic voids on the movement of galaxies is particularly noteworthy. Objects situated on the outskirts of a void experience different gravitational forces compared to those found deep within a galaxy cluster. This disparity results in the distinctive motions of galaxies as they interact with these voids. Moreover, the existence of these voids plays a key role in shaping the cosmic web, the vast network of filaments and clusters composed of galaxies and dark matter. These voids create the gaps that define this cosmic web, providing a unique vantage point for scientists to study the patterns of galaxy formation and growth over billions of years. The movement and interactions between galaxies, voids, and clusters over time have woven a complex tapestry that tells the story of the universe's evolution. These voids are not just empty spaces. Rather, they are fundamental components that influence the distribution of matter, the dynamics of galaxies, and the overall architecture of the universe. By studying these voids, scientists can uncover crucial insights into the expansion of the universe and the proliferation of cosmic structures. They serve as markers, helping researchers track the progress of cosmic evolution from the very beginning of time. The presence of these voids, stretching across the universe, offers us a deeper understanding of the forces that have shaped the cosmos as we see it today. In addition to their role in cosmic structure, voids also offer critical information about the distribution of dark matter and dark energy, two of the most enigmatic and mysterious forces in the universe. As we observe the cosmos, it becomes clear that galaxies are not randomly scattered across space. Rather, they are organized into a vast web-like structure with dense regions known as filaments interspersed with enormous empty spaces, the voids. Despite their name, these voids are not entirely devoid of matter. While normal matter is sparse, dark matter is believed to be more prevalent in these voids than previously thought. Though dark matter interacts primarily through gravity, not light, its gravitational pull is still significant in shaping the large-scale structure of the universe. Dark matter pulls galaxies toward these filaments, leaving the voids less populated in terms of ordinary matter. Dark energy, the mysterious force thought to be driving the accelerated expansion of the universe, also leaves its mark on these voids. In regions of low density like the voids, the effects of dark energy are amplified, leading to the faster expansion of these regions compared to more densely packed areas. This accelerated expansion provides valuable clues to scientists about the nature of dark energy and its role in shaping the universe's large-scale structure. By studying the characteristics of voids and their surrounding regions, researchers can better understand the interplay between dark matter, which influences the formation of the cosmic web, and dark energy, which governs the rate at which the universe expands. These studies offer a glimpse into the complex relationship between the universe's most fundamental components. The voids serve as essential markers in our ongoing quest to unravel the mysteries of dark matter and dark energy, ultimately leading to a deeper understanding of the universe's origins and its eventual fate. Voids, the enormous gaps between galaxies, also provide crucial insights into the expansion of the universe. Imagine the universe as a vast sponge, with clusters of matter scattered like granules across its surface. The areas between these clusters, where matter is relatively scarce, are where cosmic voids exist. By examining these voids, scientists are able to gather vital information about how the universe is expanding. As the universe continues to expand, galaxies move away from each other, and this movement is more pronounced in denser regions. In contrast, the voids stretch and become even less dense over time. This process gives researchers a unique opportunity to study the acceleration of the universe's expansion. The observed acceleration suggests the influence of dark energy, the mysterious force that seems to be driving galaxies apart. Through careful study of voids and their evolution, scientists can piece together a more complete picture of the forces governing the cosmos, providing key insights into the universe's expansion rate and its ongoing evolution. Voids in the universe are not just vast emptiness. They represent unique regions where the fabric of the cosmos reveals itself in surprising and profound ways. These enormous expanses of space, largely devoid of matter, offer an unparalleled backdrop against which astronomers can study the effects of cosmic expansion. The void's relatively empty nature provides scientists with an opportunity to observe the movements and positions of galaxies in unprecedented detail, unveiling the ways in which these galaxies interact with and respond to the ever-expanding universe. Understanding how galaxies shift and cluster within these voids is crucial not only for answering age-old questions about the future of the cosmos, but also for refining our models of its structure and evolution. The study of voids offers a powerful window into the dynamic dance of cosmic forces, helping us unravel how the universe unfolds and evolves, a grand spectacle that continues to reveal new layers of mystery within the vastness of space. One of the most invaluable tools in this exploration is the cosmic microwave background radiation, CMB, often called the afterglow of the Big Bang. The CMB serves as a crucial snapshot of the universe's infancy, an echo of a time when the universe was in its most primordial state. Imagine a moment when the cosmos was a hot, dense mass, filled with a glowing fog that permeated the entire space. As the universe began to expand, this fog cooled, allowing protons and electrons to combine and form the simplest elements, hydrogen atoms. This moment, known as recombination, occurred approximately 380,000 years after the Big Bang. It was at this time that photons, particles of light, were able to travel freely through space for the first time. These photons, still present today in the form of the CMB, are the faint, stretched remnants of that early universe, carrying within them invaluable clues about the conditions that existed just after the cosmos was born. The CMB is a time capsule, allowing us to peer back to a period when the universe was barely more than a glowing mist. Since then, the radiation has been stretched and cooled to a temperature just above absolute zero, and as it traverses the vast distances of space, it carries a detailed record of the universe's formation. By studying its temperature variations, scientists can gain insights into the density and distribution of matter during the universe's early years. These subtle fluctuations, while faint, tell a compelling story. They reflect the gravitational influence of matter clumping together, revealing the earliest seeds of the galaxies that would eventually shape the universe as we know it today. The CMB, in essence, serves as a cosmic map, outlining where matter was slightly denser due to gravitational pull and where it was less so, laying the groundwork for the structures that would follow. These variations in the CMB are far from random. They are the fingerprints of a universe in the midst of its formation. They reveal the subtle influences of cosmic forces, including the rate of expansion and the nature of dark energy and dark matter. By decoding these patterns, scientists have been able to reconstruct a more detailed picture of the universe's evolution, from the chaotic explosion of the Big Bang to the vast and structured cosmos that we observe today. The CMB provides essential information about the formation of large-scale structures, offering clues not only about how galaxies formed, but also about the ongoing expansion of the universe itself. However, while the CMB provides a wealth of information, it is not without its mysteries. Within this ancient radiation, scientists have uncovered a series of anomalies that challenge our current understanding of the universe. These anomalies, small variations in temperature and density observed across the sky, suggest that the universe is not perfectly uniform. Far from being a smooth and consistent expanse, the universe shows signs of early-stage irregularities, patterns that hint at the complex processes that led to galaxy formation and the large-scale structure we see today. Some regions of the CMB appear unusually smooth, while others are unexpectedly clumpy, raising questions about the mechanisms that shaped the early universe. One of the most puzzling features is the cold spot, a region of the CMB that is cooler and less dense than the surrounding areas. The nature of this cold spot has sparked a great deal of speculation. Some scientists have suggested that it could be a remnant of large cosmic structures that reshaped the very fabric of the universe, or even that it may be the result of interactions with other universes, a concept that ventures into the speculative realms of multiverse theory. While such ideas are intriguing, they remain highly speculative and outside the current consensus of cosmological understanding. The cold spot, along with other anomalies, raises questions that challenge the prevailing model of cosmology, which posits that the universe is predominantly composed of dark energy and dark matter. If the CMB contains features that don't align with our current models, it could mean that our understanding of these fundamental components of the universe may need to be re-evaluated. Each anomaly, whether small or significant, offers a doorway into deeper inquiry. They are not simply inconsistencies or problems to be solved, but opportunities for discovery, pushing the boundaries of what we know about the cosmos. As researchers continue to probe these strange signals, they find themselves unraveling increasingly complex threads of cosmic history. This ongoing investigation offers not just answers, but also new questions that could ultimately reshape humanity's understanding of the universe. From the infancy of the cosmos to the fate that lies ahead, the journey to decode the CMB is a quest to understand the deepest secrets of existence itself. The fluctuations in the cosmic microwave background are far from being random noise. These temperature variations, slight ripples on the vast cosmic pond, hold immense significance. They reveal the early structure of the universe, marking the spots where matter was slightly denser or more sparse. These variations correspond to the distribution of matter in the universe at the time, providing a blueprint for the galaxies, stars, and clusters that would form later on. High-density regions would eventually coalesce into galaxies and clusters, while lower-density regions would give rise to voids. those vast expanses of space that continue to intrigue astronomers today. By studying these fluctuations in detail, scientists can glean critical information about the universe's composition, including the relative amounts of ordinary matter, and dark energy. These fluctuations also offer insights into inflation, the rapid and expansive growth of the universe in its earliest moments. Inflation, though widely accepted, still presents many questions, and the CMB's fluctuations provide a unique signature that may help refine our understanding of this process. Moreover, the CMB also offers clues about the geometry of the universe, whether it is open, flat, or closed, helping astronomers piece together a more complete picture of the cosmos. In essence, the cosmic microwave background is like a cosmic fingerprint, a delicate and intricate pattern that reveals the universe's birth, its early evolution, and the very fabric of space-time itself. By studying these fluctuations, scientists can peel back layers of cosmic history, uncovering the story of the universe from its first moments to its present state. Yet the journey to fully comprehend the CMB is far from over. Each discovery and each anomaly adds a new dimension to our understanding, pushing us ever closer to a more complete picture of the universe's origins, its present state, and its ultimate fate. The cosmic microwave background, often abbreviated as CMB, is the faint glow that fills the universe, a remnant of the early moments after the Big Bang. This radiation is a critical piece of the cosmic puzzle, offering a glimpse into the universe when it was still a mere 300,000 years old. While the CMB's faint glow is barely detectable, it carries essential information about the conditions of the early universe. It is, in essence, a snapshot of the cosmos at a time when it was cooling and transforming into the vast expanse we now observe. The first detailed studies of the CMB revealed unexpected features that have forced scientists to re-examine existing cosmological models. One striking characteristic of the CMB is its remarkable uniformity, punctuated by slight variations, known as anisotropies, that reveal the earliest seeds of all the structures in the universe. Yet some of the patterns and temperature fluctuations observed in the CMB do not align perfectly with predictions based on the traditional inflationary model of the universe. According to this model, a rapid expansion occurred in the universe's first moments, smoothing out any irregularities. However, the unexpected discrepancies in the CMB raise intriguing questions about whether the inflationary model in its current form needs revision or further refinement. These anomalies continue to captivate scientists and enthusiasts alike, driving the search for deeper understanding of the universe's birth and its ongoing evolution. The distribution of anisotropy in the universe offers more than just clues about the structure of cosmic phenomena. It provides critical insights into the very makeup of matter and energy in the cosmos. Current cosmological models face significant challenges when attempting to align observed cosmic structures with the expected levels of dark matter and dark energy. One such anomaly involves the cold spots in the cosmic microwave background, CMB. These cold spots suggest that there may be crucial elements missing in our existing equations, elements that could provide a better understanding of how the universe functions on a grand scale. These cold patches in the CMB, which might appear as insignificant blips to the untrained eye, could in fact represent the missing pieces to a much larger puzzle, offering a hint that there are fundamental interactions occurring in the universe that we have yet to fully comprehend. The issues extend beyond just structural alignment. They touch upon the very rate at which the universe is expanding. The Hubble constant, a vital figure in cosmology, has recently presented a paradox. Discrepancies have emerged when measuring the rate of expansion using CMB data compared to measurements taken from local observations. This apparent discrepancy opens the door to many questions regarding the basic principles of cosmology. Could our assumptions about how the universe has evolved from its inception to the present be flawed? Are there hidden forces or unknown variables that we've yet to account for? These questions are far from trivial, and they compel scientists to re-examine the foundational models that govern the universe. The CMB itself remains one of the most critical tools in cosmology, providing a snapshot of the universe at a time just moments after its birth. However, as much as it illuminates the past, it also casts shadows on the present, challenging the models that once seemed solid and unquestionable. Each revelation from the CMB brings us closer to understanding the true nature of the cosmos, but it also reminds us how much more there is still to learn. The CMB acts as a faint but constant reminder that the universe is far more complex than we ever imagined, and that science is a never-ending journey into the unknown. If we take a step back and imagine the universe's early state, we can envision a scene of intense heat and pressure. In the first moments after the Big Bang, the universe was incredibly dense, filled with raw energy and particles. This early universe was a chaotic sea of radiation, constantly interacting and colliding with itself. But as time passed, the universe began to cool. Around 300,000 years after the Big Bang, temperatures had dropped enough for electrons and protons to combine and form the first hydrogen atoms. This moment of recombination was a turning point. It marked the universe's transition from being opaque to transparent, allowing light to finally travel freely without being scattered by charged particles. The radiation from this era, which we now detect as the cosmic microwave background, is a relic of this primordial moment. Today, when we observe the CMB, we are essentially seeing the faint afterglow of the baby universe, stretched and cooled by the ongoing expansion of the cosmos. What was once an incredibly hot, energetic glow has now become a diffuse, low-temperature microwave radiation that fills the entire universe. It is as if we are listening to a distant echo of the early universe, capturing the faint vibrations of a cosmos that has since evolved into what we see today. This faint radiation provides a critical window into the universe's origins, composition, and evolution, allowing scientists to peer back into the distant past, into a time when the universe was in its infancy. Black holes, on the other hand, represent some of the most extreme environments in the universe, where the forces of gravity are so intense that they can warp space and time themselves. At the very edge of a black hole lies the event horizon, the point beyond which nothing, not even light, can escape. As objects approach this boundary, they experience an increasingly powerful gravitational pull. The closer an object gets, the more stretched it becomes due to the differential gravitational forces acting on it. This stretching effect, known as spaghettification, can tear objects apart as they near the event horizon. In addition to this stretching effect, the gravitational forces near black holes also have the ability to bend light itself, a phenomenon known as gravitational lensing. This effect allows us to observe objects that are situated behind a black hole by bending the light that travels around it. The result is a warped and distorted view of the universe, where spacetime itself is bent by the extreme gravitational forces at play. Black holes are not isolated objects. They are often surrounded by accretion disks, swirling masses of gas and debris that spiral inward toward the black hole at high speeds. As these materials heat up due to friction, they emit radiation, and some black holes can even generate powerful jets of particles that shoot outward into space along the black hole's rotational axis. These jets are among the most energetic phenomena in the universe, offering a glimpse into the powerful forces that govern black holes and their surroundings. Each new discovery about black holes takes us a step closer to understanding the extreme conditions at play in these cosmic giants, while also challenging our understanding of the fundamental laws of physics. The event horizon of a black hole is a point of no return, a boundary that raises significant scientific questions about the nature of reality and the limits of our knowledge. Once an object crosses the event horizon, it becomes trapped within the black hole, unable to communicate or escape to the outside world. But this raises a profound paradox. If no information can escape from inside the event horizon, what happens to the matter that crosses it? What becomes of the information contained within that matter? The laws of quantum mechanics suggest that information should always be preserved, even if it appears to be lost. However, general relativity's treatment of black holes seems to suggest the opposite. This conflict has led to an ongoing debate among physicists about the true nature of black holes and their role in the universe. One intriguing theory that has emerged from this debate is the idea of black hole evaporation. This hypothesis suggests that black holes might not be permanent structures, but could eventually lose mass and radiate energy, potentially releasing the information they have absorbed. This concept challenges our understanding of the event horizon and raises important questions about the nature of space, time, and information itself. The paradox of escaping a black hole's gravity is perhaps one of the most profound mysteries in astrophysics. Once something crosses the event horizon, it is seemingly lost to the universe forever. But could there be ways to escape the pull of a black hole? Some scientists have speculated about quantum tunneling, a concept from quantum mechanics that suggests particles could pass through barriers they would otherwise be unable to overcome. This idea is abstract and based on the strange principles of quantum physics, but it hints at the possibility that under certain conditions, particles might be able to escape a black hole's grip in ways that we have yet to fully understand. Whether this is true or not remains a mystery, but the fact that such ideas are being considered highlights just how much is still unknown about the universe and the forces that shape it. The mysteries of black holes stretch far beyond their visible presence, deeply entwined with theoretical concepts that continuously stretch the boundaries of our understanding. One such concept is the hypothetical existence of wormholes, passages that could potentially link distant regions of space and time. If these structures were real, they might offer an escape route for information or even matter to bypass the seemingly impenetrable event horizon of a black hole, possibly defying what we perceive as an inevitable and irreversible fate. However, it's crucial to acknowledge that these ideas remain firmly within the realm of speculation. While black hole observations have provided valuable insights into their behavior and immense power, no concrete evidence has yet emerged to suggest that such mechanisms exist, nor that they could allow for any form of escape. The very nature of black holes presents one of the most perplexing challenges in physics. They force us to grapple with the intricate union of gravity, quantum mechanics, and the very fabric of space-time, resulting in an enigmatic puzzle that researchers continue to dissect. As research in this field progresses, each new discovery brings us a step closer to unraveling the true nature of black holes. This journey may one day reveal whether the prospect of escaping their gravitational grip is ever truly possible, opening the door to a radically new understanding of the cosmos. One of the most captivating phenomena associated with black holes are the immense jets of particles that emanate from their surroundings. These jets, composed of charged particles traveling at mind-boggling speeds, shoot outward from regions close to black holes, particularly from their accretion disks. The accretion disk is a swirling mass of gas and dust that forms as material is drawn in by the black hole's powerful gravitational pull. While much of this material is devoured, some of it is expelled at incredible velocities. The power and reach of these jets are remarkable, stretching across vast expanses of space far beyond the host galaxy. This phenomenon is made possible by the black hole's intense magnetic fields, which serve to channel and accelerate particles away from its immediate vicinity. To understand the scale of these jets, imagine a high-speed water hose, a forceful stream shooting particles and energy across the cosmos. But unlike a simple water hose, these jets can traverse extraordinary distances, influencing the very structure of the universe. As they travel through intergalactic space, the jets have the potential to affect the formation of stars and play a significant role in shaping the development of galaxies. Their interactions with the surrounding medium can be both destructive and constructive. Shockwaves produced by the jets can compress gas and dust, triggering the birth of new stars, thereby creating a delicate balance between destruction and creation. This remarkable interplay has made black hole jets a focal point for scientists who aim to understand how they influence cosmic evolution and the very fabric of galaxy formation. The jets themselves represent an area of intense study, offering key insights into fundamental questions about the universe, including the behavior of gravity and the evolution of galaxies. As researchers continue to explore these high-energy phenomena, black holes remain at the cutting edge of astronomical research. The mysteries they hold and the jets they produce continue to captivate both scientists and the public alike. Beyond the black hole's event horizon, a region that remains shrouded in speculation and mystery, lies a realm that could fundamentally challenge our understanding of physics. Scientists theorize that this boundary might house forms of matter and energy that defy conventional explanations. One such concept is exotic matter, substances that differ from the familiar forms of matter we encounter in our daily lives. Exotic matter is thought to have unusual properties, such as negative energy density, which could lead to strange and unpredictable behaviors in the black hole's environment. This exotic matter, if it exists, might play a critical role in shaping the black hole's internal dynamics and its interactions with the surrounding space. The process by which matter is drawn into a black hole is equally fascinating. As material spirals toward the singularity, it forms an accretion disk, an incredibly hot, rotating mass of gas and dust. The temperatures within this disk can rise to such extremes that the material emits intense radiation, particularly in the form of X-rays. This radiation serves as a valuable tool for astronomers, like allowing them to detect the presence of black holes and monitor the activity occurring in their vicinity. Furthermore, the powerful gravitational forces near a black hole can give rise to gravitational waves, ripples in the fabric of space-time that carry energy across the universe. When black holes interact or merge, they produce these waves, which can be detected even across vast cosmic distances. These gravitational waves provide new avenues for understanding the behaviors of black holes and other astronomical phenomena, offering a direct link to forms of energy that were previously undetectable. At the quantum level, researchers also delve into the concept of vacuum energy, an idea rooted in quantum field theory. According to this theory, even in the emptiness of space, fluctuations in energy may give rise to temporary particles. Near a black hole, these quantum events could interact with its powerful gravitational field, potentially resulting in the production of Hawking radiation. This theoretical phenomenon suggests that black holes might emit radiation due to quantum mechanical effects occurring near their event horizon, subtly bridging the gap between the known and the unknown. The study of such events may eventually offer profound insights into the fundamental nature of space, time, and energy. Scientists speculate that within the realm just beyond a black hole lies a unique domain of exotic matter, gravitational radiation, and quantum fluctuations, all of which invite us to reconsider the very nature of reality. These areas of research are not merely theoretical. They are active frontiers of scientific exploration, each representing a challenge to our understanding of the universe. As researchers probe deeper into these regions, the possibility of uncovering entirely new forms of matter, energy, and cosmic behavior becomes ever more tantalizing. On a broader scale, the Hubble tension represents another enigma in the field of cosmology. This debate centers around the rate at which the universe is expanding, encapsulated in the Hubble constant, a value used by astronomers to measure how quickly galaxies are moving apart. The tension arises from the fact that two different methods of calculating the expansion rate yield conflicting results. One approach involves observing nearby celestial objects, such as Cepheid variable stars and supernovae. These measurements give a direct assessment of distances and velocities, resulting in a higher value for the Hubble constant. On the other hand, estimates based on the cosmic microwave background, relic radiation from the Big Bang, produce a significantly lower value. This discrepancy between the two methods has led to what is known as the Hubble tension. The importance of this tension cannot be overstated. It poses a fundamental challenge to our understanding of the cosmos, as it suggests that our current models of cosmic expansion may be flawed or incomplete. If the Hubble constant cannot be reconciled, it could imply that there are unknown factors at play, such as new physics or previously unaccounted for forces influencing the expansion of the universe. In response, scientists are reevaluating the very constants that underpin our cosmological models. They are exploring the possibility that our assumptions about the universe, especially regarding the behavior of dark energy and dark matter, may need to be revised. This ongoing debate not only reflects the complexity of our current understanding, but also highlights the potential for groundbreaking discoveries that could reshape our view of the universe itself. As our comprehension of the cosmos continues to evolve, the search for answers remains relentless. Each new question opens the door to a host of possibilities, driving scientists to rethink everything from the deepest mysteries of black holes to the very nature of cosmic expansion. What we know today may be only the beginning of a far greater understanding as we continue to explore the vast, unknown reaches of space and time. Ultimately, the Hubble tension pushes researchers to reconsider our understanding of the universe's past, present, and future, potentially reshaping our entire perspective on its structure and dynamics. The expansion of the universe is a subject of profound intrigue for astronomers and physicists, captivating the minds of those seeking to unravel the mysteries of the cosmos. Scientists employ various methods to measure this expansion rate, each offering unique results that frequently diverge from one another, complicating our comprehension of how the universe has evolved and will continue to evolve. One of the primary methods used to measure the rate of cosmic expansion is observing distant galaxies and quantifying how rapidly they are moving away from us. This movement is intrinsically linked to the expansion of space itself, a fundamental feature of the universe's dynamic structure. However, this measurement is far from simple or definitive. When researchers apply different techniques, such as studying the cosmic microwave background, CMB radiation, or utilizing supernovae as standard candles to measure distances, discrepancies arise that cannot be easily dismissed. These differences are not just small or negligible, they represent a substantial puzzle that continues to perplex cosmologists. For instance, one method may suggest that the universe is expanding at a certain rate, while another could indicate a significantly different rate, creating uncertainty about some of the most fundamental aspects of cosmology. These inconsistencies provoke new questions, compelling scientists to consider whether our understanding of dark energy, the enigmatic force thought to be driving the accelerated expansion of the universe, is incomplete or even fundamentally flawed. Could there be aspects of dark energy's behavior that current models fail to capture? Or could new, unforeseen physics be at play that we have yet to discover? The discrepancies in measuring the Hubble constant, the rate at which the universe is expanding, raise not only technical challenges but also profound philosophical questions about the nature of the cosmos. These paradoxes spur exciting new fields of study, encouraging scientists to probe deeper into the universe's mysteries, potentially leading to a dramatic shift in our understanding of space, time, and reality itself. As researchers continue to investigate these issues, they are engaged in a search that could uncover hidden truths about the origins, evolution, and ultimate fate of the universe, potentially transforming everything we think we know about cosmic evolution. Every new mystery uncovered not only enriches our understanding of the universe, but also opens the door to deeper questions, compelling us to explore beyond the limits of our knowledge. The Hubble tension, at its core, refers to the ongoing disagreement between two primary methods for measuring the expansion rate of the universe, often described as the rate at which galaxies are moving apart. On one side, observations of the cosmic microwave background, the faint afterglow of the Big Bang, suggest a particular rate of expansion, one that aligns with earlier models of the universe. On the other side, measurements based on the distances to nearby galaxies and supernovae as standard candles show a significantly higher rate of expansion. This discrepancy is not merely academic, it's a challenge that shakes the very foundation of our cosmological models. If these two measurements cannot be reconciled, what does that mean for our understanding of the universe's composition, its history, and its future? Could this mean that dark energy, which is believed to be the force behind the accelerated expansion, behaves in a way that current models cannot account for? Or perhaps there are other, as yet unknown phenomena influencing cosmic expansion? This uncertainty casts a long shadow over our predictions about the universe's future, making the stakes incredibly high. If the higher Hubble constant is the correct value, it suggests that the universe's expansion is accelerating at an ever-increasing rate. Over time, galaxies might drift further apart, propelled by a force stronger than anything we had anticipated, leading to a future where galaxies lose sight of each other. This scenario, known as the Big Freeze, implies a cold, empty universe where, over trillions of years, the remaining stars burn out and galaxies become increasingly isolated from one another. In contrast, if the lower rate is validated, it hints at a slower pace of expansion that could, in the distant future, allow for gravitational interactions among cosmic structures. This slower expansion might allow certain structures, like galaxies, to remain bound together, altering our predictions for the universe's long-term fate. Ultimately, the Hubble tension challenges not just our measurement techniques, but the very nature of the universe itself. It forces scientists to reconsider the most fundamental aspects of cosmology, from the role of dark energy to the evolution of cosmic structures. As they work to resolve these discrepancies, they embark on a journey that could redefine our understanding of the cosmos, offering new insights that might alter our perception of reality on a cosmic scale. The Hubble constant is one of the most crucial figures in cosmology, serving as a key to understanding how quickly the universe is expanding. However, measuring this constant has become a contentious issue, with different methods leading to widely differing results. One primary technique involves observing distant galaxies and using the relationship between the brightness of certain types of exploding stars, known as supernovae, and their distances from Earth to calculate the rate of expansion. This method has suggested a faster expansion rate. On the other hand, the cosmic microwave background, which is the residual radiation from the early universe, indicates a slower rate of expansion. The disagreement between these two methods raises profound questions. If one measurement is accurate, it challenges our entire understanding of the universe's age, size, and composition. It could point to the existence of unknown factors, potentially revealing new forces or particles that have yet to be discovered. This tension is not just an academic puzzle. It challenges the very way we think about the universe and its evolution. As researchers refine their techniques and gather more data, the stakes continue to rise. Understanding the true value of the Hubble constant is not just important for theoretical physics. It holds the key to understanding the history of the universe and its ultimate fate. Gravitational waves, ripples in the very fabric of space-time, offer a new way of observing the universe. These waves are produced by some of the most violent and energetic events in the cosmos, such as the collision of black holes or neutron stars. Imagine dropping a stone into a still pond. The ripples that spread out from the point of impact are analogous to the gravitational waves created by massive objects in the universe. As these waves travel through space-time, they stretch and compress it, creating detectable disturbances. Gravitational waves were first predicted by Albert Einstein a century ago as a natural consequence of his theory of general relativity, which describes how gravity operates on a cosmic scale. However, detecting these waves has proven to be an immense challenge. Gravitational waves are incredibly faint by the time they reach Earth, often smaller than the width of a human hair. The technology required to measure them is highly sophisticated, capable of detecting minute changes with unparalleled precision. Despite these challenges, the detection of gravitational waves has opened up an entirely new frontier in astrophysics. Unlike traditional observations, which rely on light and other electromagnetic signals, gravitational waves offer a unique perspective on the universe. They allow us to study phenomena that do not emit significant light, such as the merger of two black holes, providing insights into their dynamics and the extreme environments in which these events occur. As gravitational waves continue to be detected, they hold the potential to unlock new insights into the universe's most violent and energetic processes, offering a fresh perspective on the fabric of space-time itself and revealing the hidden workings of the cosmos. The ability to study these waves may one day offer answers to questions about the universe's origins and its fate, providing a deeper understanding of the forces that shape our reality. Gravitational waves represent one of the most profound discoveries in the field of astrophysics, offering a transformative lens through which we can explore the universe. In a way that mirrors the historical revolution brought by the telescope, which unlocked the mysteries of distant stars and galaxies, gravitational waves open a new frontier in our understanding of the cosmos. These ripples, which travel through the fabric of space-time itself, are generated by some of the most powerful and energetic events in the universe, such as the violent mergers of black holes or the explosive deaths of massive stars. What makes gravitational waves particularly exciting is that they carry information about their origins that light simply cannot provide. Light, while a powerful tool in astronomy, is often obstructed by interstellar dust, gas, and other obstacles that can obscure our view of distant events. Gravitational waves, on the other hand, travel through space-time unimpeded, unaffected by the same barriers that hinder light. This means that gravitational waves offer us a rare and unparalleled view of the universe, one that enables us to witness phenomena that were once invisible to our eyes. These waves are capable of revealing secrets of the cosmos that are billions of years old, offering a clearer picture of the universe's most cataclysmic events. The detection of gravitational waves began with the development of sophisticated instruments that could measure the infinitesimally small distortions in space-time caused by these waves. These changes are so tiny that they are smaller than the size of a proton, yet they can be detected with unprecedented precision. Each detection of gravitational waves acts like a cosmic fingerprint, allowing scientists to pinpoint the origin of the waves and analyze the underlying events. For example, when two supermassive objects, such as black holes, collide, they release an enormous amount of energy, sending gravitational waves rippling across the universe. These cosmic signals can then be studied to reveal vital information about the behavior of matter and energy under extreme conditions. Gravitational waves have opened the door to a new branch of astronomy known as multi-messenger astronomy. This exciting new field combines the insights gained from gravitational wave observations with traditional electromagnetic signals, such as visible light, radio waves, and X-rays, to paint a more complete picture of cosmic events. By studying the universe through both gravitational waves and electromagnetic radiation, scientists can gain a deeper understanding of the processes that govern the universe's formation and evolution. One of the most groundbreaking aspects of gravitational wave astronomy is its ability to probe events that were once hidden from view. For example, when two black holes merge, they release an amount of energy so vast that it sends out gravitational waves capable of traveling across the universe. These waves offer a direct way to observe the black hole merger in real time, a feat that was impossible with light alone. In fact, the detection of gravitational waves in 2015 provided the first direct evidence of such a merger, confirming the predictions made by Albert Einstein's theory of general relativity. Since then, a number of other black hole mergers have been detected, each providing new insights into the properties of black holes, such as their masses, spins, and how they evolve over time. In addition to black hole mergers, gravitational waves have also provided valuable information about neutron stars. When these dense, collapsed remnants of massive stars collide, they not only produce gravitational waves, but also create heavy elements in the process. These collisions play a crucial role in the formation of elements like gold and platinum, offering important clues about the origins of these elements in the universe. By combining the data from gravitational waves with the light emitted during these events, astronomers can piece together a more complete narrative of stellar evolution and element formation. The implications of gravitational wave astronomy extend far beyond just observing distant cosmic events. By understanding the signals that these waves carry, scientists are gaining a deeper understanding of some of the most fundamental questions about the universe, including its expansion and the mysterious nature of dark matter and dark energy. These waves challenge existing theories and push the boundaries of our knowledge, prompting new inquiries into the fundamental workings of physics. As researchers continue to explore this new realm of astrophysics, gravitational waves hold the promise of radically transforming our comprehension of the universe and the forces that shape it. Looking ahead, ongoing advancements in technology and precision measurement are expected to refine our ability to detect and analyze gravitational waves with even greater accuracy. As these tools improve, we will be able to explore the universe in ways that were previously unimaginable, unlocking even more dramatic stories written in the fabric of space-time itself. The future of gravitational wave astronomy is one of immense potential, offering a new way to understand the cosmos and the violent, awe-inspiring events that have shaped it. With each new discovery, we move one step closer to unraveling the mysteries of the universe and the forces that govern it. Gravitational waves represent a monumental leap in our understanding of the universe, providing a fresh lens through which we can observe and unravel the mysteries of the cosmos. These waves, ripples in the fabric of space-time itself, offer a new way to explore the unseen phenomena of the universe, including the elusive and enigmatic realms of dark matter and dark energy. The implications of these discoveries stretch far beyond the scope of what we once thought possible, fundamentally altering how we approach cosmology and offering an unprecedented opportunity to probe the very fabric of space and time. At their core, gravitational waves are disturbances created by the acceleration of massive objects like merging black holes or neutron stars. To visualize this, imagine dropping a stone into a still pond. The surface of the water ripples outward, propagating from the point of impact. Similarly, when gigantic celestial bodies accelerate or collide, they send shock waves that traverse the universe, warping the very structure of space and time. It is through these waves that we can observe cosmic events previously invisible to traditional telescopes. Just as hearing thunder tells us about the distant lightning strike, detecting gravitational waves reveals the powerful forces that shape the universe, such as the violent mergers of black holes. The detection of these waves marks a revolutionary moment in the history of science. No longer are we limited to observing the universe through the light emitted by stars and galaxies. Instead, we now have the ability to hear the universe, opening a new realm of astrophysical research. This capability transforms our understanding of cosmic events, pushing the boundaries of what we know about the life cycles of celestial objects. It allows us to probe the universe in ways that were once confined to the realm of theoretical speculation, and every new discovery paves the way for further breakthroughs. Gravitational waves also represent a practical confirmation of Einstein's theory of general relativity, which proposed that gravity is not a force acting at a distance, as Newton had suggested, but a curvature in the fabric of space and time itself. This theory was groundbreaking in its assertion that massive objects like planets, stars, and black holes could bend the space around them, creating the effects we observe as gravity. Gravitational waves offer tangible evidence of this, providing a direct, observable manifestation of the warping of space and time caused by the movement of massive bodies. The implications of these waves extend far beyond just astrophysics. Gravitational waves introduce fascinating challenges to our understanding of gravity and force fields. Traditional theories treated gravity as a force acting over vast distances, but gravitational waves suggest that gravity can also influence objects at incredible ranges without direct contact. This shifts our understanding of gravity from a simple interaction to something far more complex, an invisible yet powerful fabric that connects the universe. Moreover, the study of gravitational waves opens up entirely new avenues for research in both astrophysics and theoretical physics. For the first time, scientists have the ability to study the aftermath of cosmic collisions, such as the merging of black holes, providing insights into the properties of these strange objects. This could also help answer long-standing questions about black holes, neutron stars, and other exotic celestial phenomena. The interplay between gravitational waves and quantum mechanics, two realms of physics that have traditionally been seen as separate, has sparked an entirely new area of inquiry. While general relativity governs the behavior of the cosmos at large scales, quantum mechanics describes the interactions of particles on the smallest scales. The detection of gravitational waves may offer a bridge between these two frameworks, offering clues about the nature of black hole singularities, those mind-bending points where gravitational forces are so intense that conventional physics breaks down. By studying how gravitational waves interact with these extreme conditions, scientists hope to uncover deeper insights into the nature of space, time, and reality itself. This merging of general relativity and quantum mechanics represents one of the most exciting frontiers in modern physics. As scientists explore this intersection, they may uncover new ways of understanding the universe and perhaps even formulate a unified theory that incorporates both the laws of gravity and quantum behavior. The study of gravitational waves not only deepens our understanding of these cosmic forces, but challenges our very conceptions of reality, pushing the boundaries of human knowledge into the unknown. Yet, while gravitational waves offer a deep dive into the mysteries of space and time, there are other cosmic phenomena that continue to intrigue and expand our understanding of the universe. Exoplanets, planets located outside our solar system, have become one of the most exciting and puzzling areas of research in recent decades. These distant worlds, some of which reside in the so-called habitable zone of their stars, offer tantalizing clues about the potential for life elsewhere in the universe. For centuries, our solar system was believed to be unique, with Earth standing alone as the only cradle for life. But the discovery of exoplanets has shattered that notion, revealing a cosmic diversity of planetary systems and challenging our understanding of how planets form and evolve. The discovery of exoplanets has prompted new questions about the conditions required for life. Some exoplanets orbit their stars in regions where temperatures could support liquid water, an essential ingredient for life as we know it. This has reignited the age-old question, are we alone in the universe? As scientists probe the atmospheres of these distant planets, they search for signs of life or the building blocks of life, biosignatures that might suggest that we are not the only life-bearing planet in the cosmos. Advances in technology, such as instruments designed to detect minute dips in starlight as exoplanets pass in front of their host stars, have revolutionized our ability to study these distant worlds. These methods allow scientists to infer properties like the size, composition, and even the atmosphere of faraway planets. Some of these planets bear striking similarities to Earth, prompting speculation about the possibility of alien life. The quest for Earth-like exoplanets, planets that could potentially harbor life, has become one of the most important and thrilling areas of scientific exploration, offering the hope of answering one of humanity's most profound questions. Are we alone in the universe? In this ever-evolving field, the discovery of gravitational waves and exoplanets are not isolated events, but part of a larger narrative about humanity's quest to understand the universe. Each breakthrough is a stepping stone, bringing us closer to comprehending the vast, complex cosmos in which we exist. These discoveries remind us that the universe is far more intricate than we once believed, and that our understanding of it is still in its infancy. With each new discovery, we push the boundaries of human knowledge further and uncover more of the cosmic tapestry that surrounds us. The mysteries of dark matter, dark energy, black holes, and the very nature of existence itself lie just beyond the horizon, waiting to be uncovered through continued exploration, curiosity, and technological innovation. The study of exoplanets offers us a profound glimpse into the past and future of our own solar system. By comparing the formation and evolution of other planetary systems with our own, we can begin to form a far more comprehensive picture of how planets come to be. This expanding field of exploration unlocks new realms of scientific inquiry, continuously challenging our understanding of the universe and the human place within it. The discovery of exoplanets, especially those with peculiar or unexpected characteristics, is a fascinating endeavor that pushes the boundaries of modern science. It merges cutting-edge technology with innovative techniques that allow us to detect these distant worlds in ways that would have seemed impossible just decades ago. One of the primary obstacles in the detection of exoplanets is their faintness, often nearly impossible to see directly, due to the overwhelming brightness of the stars they orbit. In these cases, astronomers turn to indirect methods that can infer the presence of these far-off worlds. Among the most commonly used of these techniques is the transit method. This method involves carefully monitoring the brightness of a star over a period of time. When a planet passes between us and its star, it momentarily blocks a small fraction of the star's light, resulting in a detectable periodic dimming. This brief dip in brightness provides more than just evidence of a planet's existence. It also reveals important information about the planet's size, orbit, and, in some cases, its atmospheric properties. For planets with unconventional orbits or those with unusual sizes, the distinct pattern of light dimming can offer crucial clues to their true nature, expanding our understanding of planetary diversity. Another powerful technique in the search for exoplanets is radial velocity. This method relies on observing the slight wobble of a star, which occurs due to the gravitational tug exerted by an orbiting planet. As a planet orbits its star, its gravity causes the star to move slightly, either toward or away from Earth. This shift manifests as small, periodic changes in the star's light spectrum. By measuring these shifts, scientists can detect the presence of a planet and, perhaps more importantly, infer its mass. This information allows researchers to determine the planet's density and composition, providing valuable insight into its structure and what conditions may exist on its surface. For exoplanets that lie far beyond the reach of these two techniques, astronomers turn to gravitational microlensing, a method that takes advantage of the gravitational field of a star or planet. When a massive object like a star passes in front of a more distant background star, its gravity bends and focuses the light from that star in a process known as gravitational lensing. This bending of light can reveal planets that are located at vast distances from their parent stars, or in regions where other detection methods might fail. Gravitational microlensing can also uncover planets that are situated in more unusual orbits, revealing worlds that would remain hidden using traditional observational techniques. As technology continues to evolve, advancements in space-based telescopes and sophisticated data analysis are further enhancing our ability to detect and study exoplanets. With a growing global network of scientists and institutions collaborating across disciplines, the search for exoplanets is becoming an increasingly more coordinated and efficient effort. These collaborations are helping to build a fuller picture of the incredible diversity and complexity of planets that exist beyond our solar system. Each new discovery adds another piece to the puzzle, expanding our understanding of the universe and capturing our collective imagination as we learn more about these extraordinary worlds. One particularly enigmatic class of exoplanets is that of rogue planets. Unlike the planets that orbit stars, rogue planets drift freely through the galaxy, untethered to any solar system. Their solitary existence raises intriguing questions about how they form and how they evolve. Scientists believe that some rogue planets may be the remnants of planetary systems that were disrupted, possibly due to gravitational interactions with larger celestial bodies. Such interactions could cause a planet to be ejected from its parent star's orbit, sending it into the vast, cold expanse of space where it may wander for billions of years, isolated from any star. Others may form independently, away from the influence of any star, from the same materials that give rise to stars and planets within a solar system. Understanding how these planets come into existence could offer significant insights into the dynamics of planetary systems as a whole, shedding light on the forces that govern planet formation. Rogue planets provide a unique window into how planets can form and evolve without the typical influence of a star, making them a fascinating subject of study. An even more captivating aspect of rogue planets is their potential to harbor life. While most planets are warmed and illuminated by the light of their stars, rogue planets do not have this external energy source. Yet, many rogue planets may retain warmth due to internal processes, such as radioactive decay or even residual heat left over from their formation. This heat could potentially support subsurface oceans or other environments where life, in forms radically different from what we know, could thrive. While the conditions for life on rogue planets would be dramatically different from those on Earth, the possibility remains that these solitary worlds may possess the necessary conditions for life to emerge and endure in their own unique environments. In this sense, the search for life is no longer confined to planets that orbit stars. As the boundaries of our search extend into the cold, dark reaches of space, scientists are beginning to consider the possibility that life could exist in the most unexpected of places, far from the comforting warmth of a sun. This opens up entirely new avenues of exploration, asking profound questions about the origins of life and the nature of habitable environments. Despite the challenges in detecting rogue planets, the potential number of these wandering worlds is an open question. Some studies suggest that rogue planets could outnumber the stars in our galaxy. However, quantifying their true abundance is no easy feat. Rogue planets do not emit their own light, making them incredibly difficult to observe. As a result, astronomers continue to develop innovative tools and methods for detecting these elusive objects. With each new advancement in technology, our ability to discover rogue planets improves, bringing us closer to understanding these solitary wanderers. As we explore their physical properties and atmospheres, we will likely uncover more about their unique characteristics, potentially transforming our understanding of planetary science and our place in the cosmos. As rogue planets drift through the vast expanse of the galaxy, their interactions with other celestial bodies introduce a complex web of consequences, reshaping our understanding of cosmic dynamics. These planets, which wander freely without being tethered to any star, possess the ability to disrupt the orbits of nearby stars and interfere with the delicate balance of planetary systems. As they traverse through interstellar space, they can influence the gravitational forces exerted on nearby objects, creating ripples that alter the trajectory of stars and the orbits of planets within their reach. These encounters could potentially lead to the formation of new celestial bodies or tear apart existing systems, demonstrating the profound interconnectedness of all phenomena in the cosmos. The very existence of rogue planets invites us to delve deeper into the unknown, challenging our perceptions of what we once thought possible and offering a glimpse into the unpredictable, chaotic forces that shape our universe. Their behavior raises tantalizing questions about their role in galaxy evolution, suggesting that they may play an integral part in the ongoing process of cosmic transformation. The study of exoplanetary atmospheres adds yet another layer of intrigue to our exploration of distant worlds. The atmosphere of an exoplanet serves as a cosmic detective, offering us hidden clues about the planet's origin, history, and evolution. Through the examination of atmospheric conditions, scientists can gather invaluable insights into how these planets came to be and the processes that have shaped them over time. Elements found in a planet's atmosphere, such as carbon dioxide, methane, and water vapor, act as fingerprints of its past. For instance, a significant concentration of methane could hint at biological processes, especially if found alongside oxygen in detectable quantities, suggesting the potential for life. However, methane appearing in isolation or in combination with other gases might point to entirely different chemical processes, like geological activity or volcanic emissions. Temperature and pressure, too, play pivotal roles in shaping a planet's atmosphere. Planets that orbit close to their parent stars experience intense heating, which can result in extreme weather patterns and dynamic atmospheric behavior. On the other hand, worlds located further from their stars may have cooler environments, where conditions allow for the possibility of more stable atmospheres and abundant water. Studying these planetary atmospheres enables scientists to gauge whether a planet can retain its atmosphere over long periods, or if it has lost it due to external forces like impacts from asteroids, solar winds, or radiation. The presence of clouds or storms may reveal ancient climatic shifts, telling the story of a planet's past and the dramatic changes it has undergone. A once thick, greenhouse-rich atmosphere that has since thinned out might signal cataclysmic events like asteroid impacts or large-scale volcanic activity that have forever altered the planet's climate. By piecing together these atmospheric clues, scientists begin to uncover the intricate history of these distant worlds, shedding light on the forces that have shaped their evolution and deepening our understanding of how different environments arise across the universe. Planetary systems are as diverse and varied as the stars they orbit, with some systems displaying peculiar characteristics that challenge our preconceived notions of planetary formation and dynamics. One of the most surprising revelations in recent astronomical research is the prevalence of gas giants found in very close orbits to their parent stars. For a long time, it was believed that massive gas giants would only form at great distances from their stars, where the temperatures were cool enough to allow gas to condense into solid bodies. However, many large exoplanets have been observed in tightly packed orbits far closer to their stars than we ever expected. This discovery has prompted a re-evaluation of planetary migration models, suggesting that these gas giants may have originated further out in the protoplanetary disk, but were later drawn inward by gravitational interactions with other celestial bodies or the star itself. Another fascinating anomaly in planetary system dynamics involves planets that follow highly tilted or misaligned orbits in relation to their stars' rotational axes. These misalignments are often indicative of past gravitational interactions with other massive objects, possibly other planets or rogue bodies that have since been ejected from the system or destroyed. Such gravitational encounters could have disrupted the initial orbits of the planets, leading to the observed tilts. These tilted orbits hint at a much more chaotic and dynamic early history of planetary systems than we had previously imagined, raising questions about the stability and long-term evolution of these systems. Moreover, some planetary systems exhibit extraordinary configurations, such as multiple planets that share similar orbits or demonstrate resonance with one another. These unusual arrangements challenge our understanding of planetary system stability, suggesting that the processes of formation and interaction can result in configurations that were once thought to be highly unlikely. One particularly intriguing category of exoplanets is the super-Earths, rocky planets that are larger than Earth but smaller than gas giants. The discovery of these super-Earths raises critical questions about the materials available in protoplanetary disks and the conditions necessary for their formation. Their abundance in certain regions of the galaxy challenges our current models of planetary formation and suggests that our understanding of how planets form and evolve is still incomplete. These perplexing discoveries underscore the complexity of planetary system evolution and signal that our existing models may not fully capture the dynamic processes at work within the cosmos. As new data continues to pour in from space telescopes and planetary missions, it becomes increasingly clear that each new discovery has the potential to reshape our understanding of how planets form, interact, and evolve across the vast expanse of the universe. The more we learn, the more we realize that the cosmos is far more complex and unpredictable than we had ever anticipated. Time, too, behaves in a manner that defies our usual understanding when viewed through the lens of cosmic scales. At the subatomic level, time seems almost irrelevant, as particles flicker in and out of existence within mere fractions of a second. The fleeting interactions of these particles occur so rapidly that they evade our everyday experience of time, making it challenging to conceive of events in ways that align with our perception of the passage of time. As we scale up to planetary and stellar systems, time becomes more familiar. On Earth, we experience time through the rhythmic cycles of day and night, governed by the planet's rotation. Stars, on the other hand, live for millions to billions of years, their life cycles unfolding at such vast timescales that human minds struggle to grasp their full extent. This vast span of time, stretching over eons, introduces the concept of cosmic time, a timeline that does not align with our daily, earthbound experience of time. In the context of the cosmos, time is not constant. It stretches and compresses depending on the context in which it is measured. One striking example of this phenomenon is the effect of gravitational fields on the passage of time. According to Einstein's theory of general relativity, time slows down in regions of intense gravity. This concept, known as gravitational time dilation, has been observed in practice, as clocks in stronger gravitational fields tick more slowly compared to those in weaker fields. This idea challenges our understanding of time as a constant and reveals that the fabric of space itself influences the rate at which time passes. Furthermore, the theory of relativity also suggests that time behaves differently for objects moving at high velocities. As an object approaches the speed of light, time slows down relative to an observer in a stationary position. This effect, known as time dilation, has been demonstrated in experiments with particles moving at relativistic speeds, and it offers a profound insight into the relationship between space, time, and motion. For those aboard a spaceship traveling near the speed of light, time would seem to pass normally. However, to an observer on Earth, the clock on the spaceship would appear to tick slower. These paradoxes in the perception of time not only challenge our everyday understanding, but also highlight the profound and mind-bending nature of the cosmos. Time is not a simple linear progression. It is a complex, fluid concept, intricately woven into the fabric of the universe itself. Gravity, in its vast and mysterious power, plays a fundamental and astonishing role in time dilation. It's an extraordinary phenomenon that defies our conventional understanding of time. In regions with stronger gravitational fields, such as those near massive celestial bodies like planets, stars, or even black holes, time itself slows down. The closer you get to these dense objects, the more pronounced this effect becomes, creating a reality where time passes more slowly compared to areas where gravity is weaker. It's almost as if gravity acts as a cosmic timekeeper, dictating the pace at which time moves, with the most extreme time differences occurring near the heaviest masses in the universe. This concept isn't just a theoretical curiosity or abstract physics, it's something with real, practical consequences. One of the most visible and tangible examples can be found in the technology we use every day, particularly in the functioning of GPS satellites. These satellites orbit the Earth in regions where gravity is weaker, causing their onboard clocks to tick faster than those on the ground, where gravity is stronger. Scientists must account for this difference in time to ensure the accuracy of location data. In a sense, this principle of time dilation is woven into the very fabric of modern technology. However, the most captivating and mind-bending aspect of time dilation lies in its implications for human experience. Imagine a pair of identical twins, one remaining on Earth, and the other journeying through space at a speed close to that of light. Upon their reunion, the twin who traveled through space would be far younger than the one who stayed on Earth. This scenario, based on the principles of relativity, raises profound questions about time itself. It forces us to reconsider the notion that time flows in the same way for everyone, everywhere, at all times. It challenges the fundamental assumptions about the passage of time and what it means to age. Such paradoxes and mysteries drive scientists to push the boundaries of our understanding. Every new discovery opens doors to more questions, inviting us to explore the very essence of reality. What is time, really? How does it shape the universe, from the birth of stars to the ultimate fate of galaxies? These questions fuel our exploration of the cosmos and our quest for knowledge that could forever alter our perception of the universe itself. At the heart of time dilation lies Albert Einstein's groundbreaking theory of relativity. This theory reshapes our entire understanding of time, revealing that it's not a constant as we once believed. Instead, time is flexible, elastic even, capable of stretching and compressing depending on both the speed at which an object moves and the strength of the gravitational field it's in. The faster you move, the slower time passes relative to someone at rest. The stronger the gravitational field, the more time dilates. Time, in this sense, is not a uniform experience shared by all, but a malleable concept that shifts based on the conditions we find ourselves in. To truly grasp this, imagine two observers. One stands still on Earth, while the other moves at an incredible speed, perhaps traveling in space at a velocity close to that of light. The observer on Earth would age at the normal rate, while the traveler would experience time in a completely different way. For them, time would seem to pass more slowly, meaning they would return to Earth after what feels like only a short time for them, while their counterpart on Earth would have aged far more. This stark contrast between their experiences highlights the reality of time dilation and underscores the fluidity of time itself. Delving deeper into the concepts of time, we also encounter the fascinating idea of time loops and paradoxes, themes that are frequently explored in theoretical physics and cosmology. Time, in this context, is often envisioned as a river flowing in one direction. In most situations, this river flows forward, with events happening in a straight line, just as droplets fall downstream. However, the concept of a time loop introduces a twist. Certain sections of this river might curve back on themselves, allowing events to potentially repeat or return to earlier points in time. It's as if the flow of time itself could fold upon itself, creating a cyclical nature that allows for repetition. This possibility of closed time-like curves, a concept discussed in relation to time travel, suggests that it may be possible to travel through these bends in the fabric of space-time and return to a previous moment. Imagine walking in a circle on a flat surface. If time were structured similarly, you could eventually find yourself at a past moment in your life. This raises profound questions about causality, the principle that every effect must have a preceding cause. If you were to travel back in time, your actions could alter the events that came before, potentially leading to a paradox. A well-known example of this is the grandfather paradox. If someone traveled back in time and prevented their grandfather from meeting their grandmother, How could they have ever existed in the first place to make such a trip? Such paradoxes expose the inherent contradictions in the concept of time travel and challenge our understanding of cause and effect. To resolve these paradoxes, some theorists propose the idea of parallel universes or multiple timelines, suggesting that every decision or alteration could create a new branch in the timeline, thereby sidestepping any impossible contradictions. These alternative realities would allow the original timeline to continue unaffected, while the new timeline branches off in a different direction. The idea of multiple timelines opens up a world of possibilities and challenges our basic assumptions about the structure of reality itself. The theoretical exploration of time travel, black holes, quantum mechanics, and the fundamental nature of the universe is ongoing, and much of it remains speculative. Yet these ideas continue to inspire and captivate our imagination, pushing us to think about the universe in ways that stretch beyond our everyday experiences. Time, it seems, is not just a measurement of moments, but a dynamic force that shapes the very fabric of existence. Time is not only central to the study of the cosmos, but is a defining feature of our experience as human beings. From the Big Bang, which marked the birth of everything we know, to the eventual end of everything, time is the thread that weaves the story of the universe. Our understanding of time has evolved over centuries, and as we continue to explore the universe, we are discovering new dimensions to this fundamental aspect of reality. The progression of time, as we experience it, appears linear, moving from past to present and toward the future. This linear flow of time is central to cosmology, as it governs the evolution of the universe. As the universe expands, galaxies move farther apart from each other, a phenomenon that has been observed over many years and is a key piece of evidence supporting the idea of an expanding universe. The continued acceleration of this expansion could lead to a scenario known as the heat death of the universe. In this distant future, stars would burn out, leaving behind a cold, dark cosmos where matter is so widely dispersed that no meaningful interactions could take place. It would be a universe devoid of light, energy, and life, a silent testament to the passage of time and the eventual entropy that consumes all things. The unfolding of time, from the birth of stars to their eventual demise, from the formation of galaxies to the ultimate fate of the universe, offers profound insights into the nature of existence itself. The study of time, both in its passage and in its potential distortions, offers us a glimpse into the very heart of reality. It's a journey that continues to unfold, revealing new mysteries, new possibilities, and an ever-deepening understanding of the universe we call home. Conversely, if the expansion of the universe were to slow down and ultimately reverse, it could trigger a dramatic event known as the Big Crunch. This scenario suggests that time itself could reverse, drawing everything in the cosmos back together until the universe collapses into an infinitely dense point, a singularity. In this chaotic reversal, galaxies, stars, and planets would be torn apart and crushed into the singularity, erasing any trace of what once was. This cyclical notion of the universe is not merely speculative. It hints at a deeper, ongoing narrative through time, one where the concept of beginnings and endings is far from definitive. Instead, these events could merely be phases in an eternal loop, suggesting that the universe may undergo infinite cycles of birth, collapse, and rebirth. The cyclical universe model challenges our traditional understanding of existence, indicating that time and space are not linear, but are part of a dynamic and recurring process. On the other hand, in an alternative scenario, time could stretch on indefinitely as the universe continues to expand forever, causing everything within it to drift apart. In this endless expansion, galaxies and stars would grow increasingly isolated from one another, and the fabric of space itself might weaken, eventually leading to the dissipation of all matter and energy. This scenario envisions an eternity of vast, empty nothingness, where all that remains of the cosmos is cold, scattered particles, endlessly separated in a dark and desolate universe. Time, in this case, would carry on as an eternal witness to the universe's slow, inexorable fading into oblivion. This picture of an ever-expanding universe without end presents a chilling possibility for the ultimate fate of everything that exists. In both of these possibilities, whether the universe collapses or continues to expand into emptiness, time remains the central thread weaving through the narrative of existence. It shapes how we understand ourselves and everything around us. The passage of time provides the context for our origins, our transformations, and our eventual endings. Time is the canvas on which the universe paints its story. Regardless of how the universe unfolds, time provides the framework that allows us to conceive of existence itself, shaping our perception of what was, what is, and what might be. The concept of the arrow of time is central to this understanding, a philosophical and scientific idea that describes how time appears to move in a specific direction, forward. From the past to the present and onward into the future, this directional flow of time governs our daily experience. Yet, this seemingly simple concept presents a profound puzzle for scientists. Unlike space, where we can move in any direction, up, down, left, right, forward, backward, time flows in one direction only. This asymmetry raises fundamental questions about why time seems to be so different from space in this regard. At the heart of this enigma lies the second law of thermodynamics, which asserts that in an isolated system, disorder tends to increase over time. This is often illustrated by the example of a glass of ice melting in a warm room. Initially, the system is orderly, with ice at a low temperature and water at a higher one, but as time progresses, the ice melts, the heat disperses, and the system becomes more disordered. This tendency towards increasing disorder, known as entropy, helps explain why we perceive time as moving forward. In other words, the movement from order to disorder defines our experience of time. However, the laws of physics do not inherently favor one direction of time over another. The fundamental equations that govern the forces of nature, whether gravitational, electromagnetic, or nuclear, are time-symmetric, meaning they treat both directions of time equally. This creates a paradox. If the laws of nature are neutral about the direction of time, why do we experience time as always flowing forward? This contradiction between the symmetry of physical laws and the one-way flow of time is a mystery that continues to perplex scientists and philosophers alike. An additional layer of complexity arises when we consider the role of consciousness in our perception of time. Our memories, formed from past experiences, create a narrative that reinforces the idea that time has a clear direction. As we recall events, we construct a story in which the past leads into the present, and the present moves into the future. This subjective experience of time as a flowing entity could, in part, be a feature of human consciousness, not an inherent quality of the universe itself. Our perception of time may be more a reflection of how we observe and interpret events rather than a fundamental characteristic of reality. Moreover, theories of special and general relativity, developed by Albert Einstein, add further dimensions to our understanding of time. According to these theories, time is not a constant, universal experience, but can be influenced by factors such as speed and gravity. For instance, the faster an object moves relative to another, the more slowly time passes for it, a phenomenon known as time dilation. Similarly, time passes more slowly in stronger gravitational fields. This flexibility of time complicates the notion of a universal arrow of time. Depending on the observer's relative circumstances, time can appear to move differently, undermining the idea that time flows in one consistent direction for all. The arrow of time remains one of the most intriguing mysteries in modern physics because it intertwines fundamental principles of thermodynamics, consciousness, and the nature of space-time itself. Scientists are still grappling with the question of why we experience time as a continuous flow in one direction. Understanding how this perception relates to the underlying laws of the universe could have profound implications for our understanding of reality. Supermassive black holes, those enigmatic giants that often lurk at the centers of galaxies, also play a crucial role in the evolution and behavior of the cosmos. These massive entities can be billions of times heavier than the Sun and exert an incredibly powerful gravitational influence on their surroundings. As matter, gas, dust, stars, and even entire solar systems draws closer to a supermassive black hole, it is pulled into an accretion disk, a swirling mass of particles that accelerates to extreme speeds. In this disk, material heats up, emitting radiation across a broad spectrum of wavelengths from visible light to X-rays. The energy generated by this process can have significant consequences for the galaxy as a whole. The intense radiation and powerful jets of particles emitted by the black hole can contribute energy and momentum back into the galaxy, impacting star formation. In some cases, the energy released is so great that it can suppress star formation in the region surrounding the black hole, creating a feedback loop where the black hole and the galaxy influence each other's evolution. Furthermore, the gravitational influence of the supermassive black hole acts as a kind of cosmic glue, stabilizing the galaxy's core. By controlling the movement of stars and gas near its center, the black hole helps maintain the overall structure of the galaxy. It affects the orbital patterns of stars in its vicinity, resulting in unique and predictable motion that can be observed by astronomers. In this way, supermassive black holes not only shape their immediate environment, but also contribute to the broader dynamics of their entire galaxy, marking them as essential players in the cosmic drama. Supermassive black holes hold a unique and profound significance in the grand scale of the universe. These cosmic giants, whose masses can range from millions to billions of times that of our Sun, are not merely passive remnants of ancient stellar events. Instead, they actively influence the very fabric of their host galaxies, shaping their growth, evolution, and fate over vast stretches of cosmic time. At the heart of this influence lies a crucial relationship. The mass of a supermassive black hole is closely linked to the overall mass of its galaxy. As galaxies grow, their central black holes often grow in tandem, but not in isolation. The development of a galaxy is intricately tied to the dynamics of its black hole. These supermassive entities do not merely sit idly at the centers of their galaxies. They are active participants in the processes that either promote or hinder the galaxy's growth. Through their gravitational influence, they can regulate star formation, suppress gas inflows, or trigger conditions that encourage the formation of new structures. Some researchers propose that this delicate interaction between the black hole and its host galaxy is central to determining the type of galaxy that emerges, whether it evolves into a spiral galaxy with its graceful, winding arms, or an elliptical galaxy, a more spherical and often more stable form. This hypothesis suggests that the nature of the black hole's growth and the feedback mechanisms it generates may determine whether a galaxy will spiral outward in elegant arms or collapse into a dense elliptical shape. These interactions help explain the diverse array of galaxy structures observed across the universe, from the sprawling pinwheel-like arms of the Milky Way to the tightly packed elliptical galaxies scattered throughout the cosmos. The early universe, a time long before galaxies had fully formed into the structures we recognize today, presents an even more intriguing puzzle when it comes to supermassive black holes. Their rapid formation, occurring only a few 100 million years after the Big Bang, defies conventional expectations. In a universe that was still densely packed with gas and matter, these colossal black holes seem to have emerged much faster than theories would suggest. The traditional model for black hole formation involves the collapse of massive stars, but such a process would take billions of years, far longer than the relatively short period available in the early universe. This raises the question, how could supermassive black holes form so quickly? Some theorists have proposed that these early black holes might not have formed through stellar collapse at all. Instead, they could have arisen from the direct collapse of massive clouds of gas. This scenario bypasses the typical stages of star formation, allowing the black holes to form much more rapidly. The conditions in the universe immediately after the Big Bang were extreme, with a dense, hot mix of particles and radiation. In this chaotic environment, gas clouds could collapse under their own gravity, directly forming supermassive black holes. This theory aligns with some of the earliest observations of quasars, extremely bright energetic objects powered by supermassive black holes that have been detected at staggering distances, corresponding to times when the universe was still in its infancy. Yet even more puzzling than the formation of these supermassive black holes is the speed at which they grew. To become truly supermassive, a black hole must consume vast amounts of surrounding material. How, in the early universe, could there have been enough gas and dust for these black holes to accrete so much mass in such a short period? Some researchers suggest that the rapid growth of these black holes could be explained by the presence of abundant gas clouds, rich in the raw materials needed for accretion. These clouds might have been drawn in by the gravitational pull of the black hole, fueling its growth at rates far exceeding what is observed in the present-day universe. Quasars, the brilliant beacons of light emitted by supermassive black holes, provide key evidence for the existence of these rapid growth processes. Observations of distant quasars show that they were active when the universe was still very young, implying that the conditions necessary for such rapid black hole formation were present at an early stage. For these black holes to shine so brightly, they must have had a continuous supply of matter, gas, dust, and possibly dark matter, feeding into them at astonishing rates. Further theories suggest that the rapid growth of supermassive black holes could also involve the merger of smaller black holes. In this scenario, multiple black holes might have collided, combining their masses to form even larger, more powerful black holes. Another possibility is that massive inflows of gas could have been funneled into existing black holes at unprecedented rates, accelerating their growth. These rapid accretion events would have been accompanied by intense radiation, further contributing to the black hole's brightness and providing critical clues about their early formation. The relationship between a supermassive black hole and its host galaxy is also influenced by the surrounding environment, particularly the mysterious dark matter that makes up a significant portion of the universe's mass. Dark matter, unlike ordinary matter, does not emit or absorb light, making it invisible to conventional telescopes. Yet, its gravitational influence is undeniable. In regions close to a supermassive black hole, the effects of dark matter can be profound. The gravitational pull of the black hole, combined with the dense clusters of dark matter surrounding it, alters the movement of stars, gas, and other matter within the galaxy. This combined gravitational well helps draw in surrounding material, making it easier for the black hole to capture and consume new matter. Dark matter's role in the development of galaxies and supermassive black holes is a subject of ongoing investigation. Although it cannot be directly detected, its effects on the behavior of visible matter are crucial to understanding how galaxies evolve. In the case of a supermassive black hole, the presence of dark matter may help facilitate the inflow of gas and dust that sustains the black hole's growth. The interaction between dark matter and visible matter, especially near the central black hole, provides a subtle but significant force in the overall dynamics of a galaxy's development. As astronomers continue to develop new technologies and advanced simulations, the mysteries surrounding supermassive black holes are gradually coming into focus. Powerful telescopes and sophisticated computer models allow scientists to peer back in time, observing the oldest galaxies and the supermassive black holes that reside at their cores. These observations help unravel the complex relationships between black holes, galaxies, and the larger cosmic environment. Still, many questions remain. How exactly did these black holes grow so rapidly in the early universe? What role did dark matter play in their formation and evolution? How did the interplay of gravity, radiation, and gas contribute to their astonishing growth? Despite the progress that has been made, much of the story remains obscured, hidden in the depths of space and time. However, each new discovery brings us closer to understanding the intricate dance between black holes, galaxies, and the vast cosmic forces that shape the universe. Supermassive black holes, once thought to be passive relics of the distant past, have proven to be far more dynamic. They are integral to the evolution of galaxies, influencing their structure, growth, and even their eventual fate in the vast expanse of the universe. As our knowledge of these cosmic giants deepens, we continue to uncover the profound ways in which they shape the universe, contributing to the complex, interconnected web of forces that define the cosmos. As galaxies continue to evolve and collide, the massive regions known as dark matter halos, vast areas filled with the elusive substance dark matter, begin to interact with one another. This interaction isn't just a passive encounter, but a dynamic process that can dramatically reshape both the galaxies involved and the universe itself. When these halos collide, they funnel additional gas and dust into the supermassive black holes nestled at the centers of many galaxies, feeding them and enabling these dark behemoths to grow ever larger. This process reveals how interconnected the various cosmic elements are, and how the gravitational forces of supermassive black holes can impact the distribution of dark matter itself. Such forces could release vast amounts of energy, potentially influencing the large-scale structure of the universe, hinting at a deeper and more complex relationship between matter we can see and matter we cannot. Supermassive black holes don't exist in isolation. They interact in a delicate and intricate gravitational dance with dark matter. Together, they shape the very structure of galaxies and even the fabric of space-time itself. It's a complex and ongoing balancing act, where the forces at play determine not only the fate of individual stars and galaxies, but also the dynamics of the universe as a whole. By understanding this relationship, we unlock new insights into the interaction between visible and invisible matter, two forces that work in tandem to create the universe we observe. The growth of these titanic objects, supermassive black holes, has long been a captivating area of research in astrophysics, with a wide range of theories attempting to explain how these colossal entities formed and evolved. One of the most prominent hypotheses is that supermassive black holes are the result of smaller black holes merging over time. These smaller black holes could be remnants of once massive stars that ended their lives in explosive supernovae. As these smaller black holes collide and merge, they can grow in size, feeding off surrounding matter, gravitationally attracting new gas and stars, and gradually building the massive black holes we see at the centers of galaxies today. Another intriguing theory suggests that supermassive black holes may have formed directly from vast clouds of gas in the early universe. In this scenario, conditions in these dense clouds allowed them to collapse under their own gravity, eventually leading to the creation of a black hole at their core. This model, known as direct collapse, posits that primordial black holes formed from these dense gas clouds could have evolved into the supermassive giants we observe today, particularly in the environments of young and active galaxies where gas was abundant. In addition to these theories, another line of thought focuses on the role of rapid accretion, the process in which black holes consume gas, mass, and stars at incredibly high rates. This process can lead to explosive growth periods, with black holes generating vast amounts of energy and radiation, often making them difficult to observe during their formative stages. As these black holes rapidly accumulate matter, the energetic feedback from forming stars and active galactic nuclei can heavily influence their growth. The balance of material falling in and being expelled outward becomes a key factor in the development of these objects. Some researchers have proposed that supermassive black holes could form through a combination of these mechanisms: mergers, direct gas collapse, and efficient accretion, each process interacting dynamically as galaxies evolve. This multifaceted approach highlights the complexity of how supermassive black holes can develop, showcasing the diversity of possible scenarios and the ongoing effort to understand these enigmatic entities. As new theories and observations emerge, they offer fresh avenues for exploration, pushing the boundaries of our knowledge and deepening our understanding of the universe's most mysterious objects. Supermassive black holes are not just solitary, inert points in space. They play an essential and intricate role in shaping the vast structures of the universe. Their influence extends far beyond the galaxies in which they reside, affecting everything from the formation of stars to the distribution of dark matter. At the heart of each galaxy, a supermassive black hole acts as an anchor, holding entire galaxy clusters in place, much like the central support in a massive structure. As matter falls into these black holes, it doesn't simply vanish into the abyss. Instead, it generates immense amounts of energy, often in the form of powerful jets and winds that can influence star formation within their host galaxies. These jets of energy can either promote star formation by compressing gas and dust, encouraging it to collapse and form new stars, or they can hinder star formation by blowing away the gas and dust that would otherwise coalesce into new stars. The energy generated by supermassive black holes can thus have a profound effect on their host galaxies, dictating whether they thrive with new stars or stagnate, deprived of the material needed for further stellar birth. This interaction doesn't stop at the galaxy level. The energy and material expelled by supermassive black holes can ripple through the cosmos, influencing neighboring galaxies and even larger cosmic structures. These effects can have wide-reaching consequences for the evolution of galaxies, galaxy clusters, and the entire large-scale structure of the universe. The relationship between supermassive black holes and the galaxies they inhabit is thus far from a one-sided affair. It is a dynamic and ongoing interaction that shapes the future of the cosmos itself. Through these processes, supermassive black holes continue to fuel a cosmic cycle of creation, destruction, and transformation, influencing the universe in ways that are only beginning to be understood. Each discovery brings us closer to unraveling the mysteries of these colossal forces, and in turn, the mysteries of the universe they help shape. The journey to understand these objects is a never-ending quest, but it is one that offers profound insights into the fundamental forces governing the cosmos and our place within it. Observations have consistently shown a compelling connection between the mass of supermassive black holes and various key characteristics of their host galaxies. These include factors such as the rate of star formation and the overall size of the galaxy. This intricate relationship suggests a fascinating idea. Black holes and galaxies do not merely exist in isolation, but rather evolve together, shaping and influencing one another throughout the vast stretches of cosmic time. The interplay between these two entities is far from a mere happenstance. Rather, it forms a dynamic and ever-evolving process. On a much grander scale, supermassive black holes are not confined to individual galaxies. They serve as central pillars within galaxy clusters, which are among the largest gravitationally bound structures in the universe. Their gravitational influence helps shape the structure of the cosmos itself, including the formation of the cosmic web, a vast and intricate network of galaxies interconnected through dark matter. The cosmic web, often described as a sponge-like structure, showcases the profound influence of supermassive black holes in the formation of the universe's largest scale features. As they alter the distribution of matter throughout space, they play an essential role in shaping not only individual galaxies, but also the immense architectures of galaxy clusters. Far from being isolated phenomena, supermassive black holes are central players in the grand evolutionary drama of the cosmos, sculpting the very structures that define the universe. Their influence extends from the smallest scales of individual galaxies all the way to the colossal configurations of galaxy clusters, constantly interweaving with the larger story of cosmic evolution. As we peer outward to the farthest reaches of the observable universe, we encounter a vast, unfathomable expanse filled with mystery and uncertainty. This boundary, the farthest point from which light emitted after the Big Bang has had time to reach us, represents the edge of our cosmic vision. Beyond this limit lies a region that remains unseen, an enigmatic realm that raises countless questions about what might lie there. One of the primary mysteries at the heart of this boundary is related to the incredible uniformity of the early universe. Despite the apparent chaos and variety that we observe today, the cosmic microwave background radiation reveals that the early universe was strikingly homogeneous, uniform in ways we are still working to understand. The question arises, how did these uniform conditions, so neatly ordered in the beginning, evolve into the intricately complex structures we see today, galaxies, clusters of galaxies, and the vast interconnected web that binds them together? This puzzle becomes even more intriguing when we consider the possibility that there might be regions beyond our observable universe with entirely different properties. Could these far-flung regions hold clues about the very nature of the universe itself? Could they offer insights into the forces and dynamics that shape the cosmos long before the birth of our own galaxy? Beyond this, the notion of the multiverse, that our universe might be just one of many, each with its own unique set of physical laws and constants, presents an entirely new level of intrigue. If this theory holds any weight, then what lies beyond our observable universe might be a realm entirely foreign to us, untouched by the fundamental forces that govern our experience. This notion introduces tantalizing possibilities, suggesting that the universe we know is but a single thread in a vast and varied cosmic tapestry. Compounding the mystery are the elusive phenomena of dark matter and dark energy, two forces that together account for the majority of the universe's mass energy content, yet remain shrouded in mystery. Dark matter, an invisible substance, is detectable only through its gravitational effects on galaxies and other cosmic structures. While it does not emit light or energy, its influence on the cosmos is undeniable. In much the same way that a hidden object can be inferred by observing the movement of nearby objects, dark matter reveals its presence through its impact on the larger cosmic structure. Meanwhile, dark energy, the mysterious force believed to be driving the accelerated expansion of the universe, adds another layer of complexity to our understanding of the cosmos. This force is elusive, remaining undetectable by direct means, yet its influence is fundamental to the ongoing expansion of space. Picture the universe as a balloon being inflated. Dark energy acts as the unseen air pushing it outward, influencing the movement of galaxies and driving them ever further apart. Looking even further beyond our observational capabilities, we encounter the possibility of even more exotic and enigmatic phenomena, such as primordial black holes. These hypothetical black holes, which could have formed in the very early stages of the universe, tantalizingly remain just out of reach of our detection methods. Depending on their size, primordial black holes could hold vital clues about the conditions that existed in the early cosmos, offering a window into the universe's infancy, a time when the very first seeds of structure were taking root. At the farthest edge of our perception, the observable universe itself serves as a profound threshold, an opening to both knowledge and imagination. Each discovery that nudges us closer to this boundary brings us one step further toward a deeper understanding of the universe and its intricate mysteries. But even as we push the limits of what we can observe, the sheer scale and complexity of the cosmos suggests that much more lies beyond our reach, waiting to be discovered. The boundaries of the observable universe are defined by a delicate interplay of factors, including the nature of light, the expansion of space, and the technologies at our disposal. When we look into space, we are, in a sense, looking back in time. Light from distant celestial objects takes years, often millions or billions of years, to reach us. As a result, the farther away we look, the earlier in the universe's history we are witnessing. This phenomenon means that our view of the universe is limited not only by the distance that light can travel, but also by the constraints of our observational tools. The observable universe is often described as a vast bubble surrounding Earth, extending outward to the farthest points from which light has had time to reach us since the Big Bang. Within this bubble are galaxies and cosmic phenomena that have existed for billions of years. However, the edge of this observable universe marks a boundary beyond which light has not yet reached us. Anything beyond this region remains invisible, hidden in the shadows of time and space. The universe is not static, though. Space itself is expanding, meaning that galaxies are moving away from us, and the light they emit is becoming increasingly redshifted. As this redshift stretches the light to longer wavelengths, galaxies may eventually move beyond the limits of our detection capabilities, making them seem as though they are disappearing from view. This cosmic expansion is not just a theoretical concept, it is an observable phenomenon, one that underscores the dynamic, ever-changing nature of the universe. Our ability to observe the universe is also limited by the technological tools at our disposal. Telescopes, for example, have specific capabilities, determining the faintest and most distant objects that we can identify. However, with each new generation of instruments, ranging from radio telescopes to space-based observatories, our view of the cosmos expands. These advancements in technology allow us to capture light across a broader range of wavelengths, from the longest radio waves to the shortest gamma rays. As our instruments evolve, so too does our understanding of the universe, enabling us to paint an ever-expanding picture of the cosmos. The boundaries of our cosmic sight are defined by several factors: the speed of light, the expanding nature of space, and the ever-evolving technology that allows us to peer deeper into the universe. Yet, just beyond our current observational reach lies a realm of untapped potential. The phenomena that exist there, dark matter, dark energy, primordial black holes, and others, have the potential to reshape our understanding of the universe. As we continue to push the boundaries of our knowledge, we may one day uncover secrets that will alter our fundamental understanding of the cosmos itself. Moreover, there may be entire regions of space where the very laws of physics, as we understand them, break down or behave in unexpected ways. These anomalies could give rise to phenomena that defy prediction or comprehension. As we advance technologically and refine our methods, these enigmatic aspects of the cosmos are likely to be uncovered, offering new insights that could rewrite the very narrative of the universe. Each new discovery serves as a window into a reality that challenges our fundamental understanding of space, time, and existence itself. It forces us to reconsider what we thought we knew, pushing the boundaries of human knowledge and forcing us to confront the unknown. The concept of the cosmic horizon, for instance, radically transforms our perception of infinity. This horizon places a boundary on the observable universe, framing infinity within the limits of what we can perceive. It is akin to standing on a vast, endless beach and gazing out over the ocean. The horizon is a line that separates the known from the unknown. If you were to venture beyond that point, you could discover more, but only up to a certain extent. The same principle applies to the universe. The cosmic horizon marks a limit to how far we can observe. This limit exists because the speed of light is finite, and as the universe expands, light from distant galaxies takes time to travel to us. This cosmic horizon defines the edge of our observable universe. Beyond this boundary, light has not had the time to reach us since the beginning of the universe, roughly 15 billion years ago. It implies that there are countless galaxies and cosmic phenomena beyond our reach, hidden from our observation. Although infinity suggests an endless expanse, our understanding of the universe is constrained by this horizon, creating a paradox. The universe may be infinitely large, yet we can only comprehend a small fraction of it. This paradox raises a host of intriguing questions. What lies beyond the cosmic horizon? Are there entire galaxies, star systems or perhaps entirely new structures of matter and energy that we can't even begin to imagine? The very notion of a cosmic horizon compels us to rethink the scale and structure of the universe itself. It suggests that while the universe could be infinite, our experience of it is fundamentally limited. The vast, unfathomable complexity of the cosmos is, in essence, forever beyond our full grasp. The more we explore, the more we realize how little we truly know. The edge of the observable universe is a profound focal point in cosmology. It's not just a boundary in space, it represents a boundary in time as well. The light that reaches us from the furthest corners of the cosmos has traveled for billions of years. The cosmic horizon is not merely a spatial edge, it is the furthest light that has had the time to reach us since the universe became transparent. It marks a moment in the universe's timeline, a crucial threshold after which the universe's first light broke free, roughly 15 billion years ago. Beyond this boundary lies a realm that is, for now, completely hidden from us, shrouded in cosmic mystery. Yet the potential for discovery at the edge of the universe is enormous. As we push the limits of what we can observe, any breakthrough could radically shift our understanding of the cosmos. Imagine the consequences of finding evidence for structures or phenomena that challenge current models of cosmology. If, for example, scientists were to uncover new forms of matter or energy beyond the known spectrum, it could prompt a fundamental rethinking of the universe's composition. This might signal the need for new theoretical frameworks that move beyond our reliance on concepts like dark matter and dark energy, concepts established to explain what we cannot see. Moreover, delving into the cosmic horizon could provide crucial clues about the very expansion of the universe. If researchers were to uncover discrepancies in the rate at which the universe is expanding, it could open the door to new theories about the forces driving cosmic growth. Such a discovery might even lead to the identification of new physical laws, altering our understanding of the cosmos at its most fundamental level. One particularly fascinating aspect of this edge is the cosmic microwave background, CMB, the afterglow of the Big Bang. This relic of the early universe offers a snapshot of conditions just moments after the universe began. By studying anomalies in the CMB, scientists could refine their understanding of the universe's origins and potentially rewrite the timeline of cosmic history. These insights could lead to a radical shift in how we understand the evolution of the universe, from its explosive birth to its current, ever-expanding state. Each new discovery at the universe's edge brings with it an opportunity to rethink established theories. With the aid of advanced telescopes and cutting-edge technology, we are now able to peer deeper into the cosmos than ever before. Every breakthrough, no matter how small, adds to our collective understanding, driving the ongoing quest for knowledge. As we gather more data, it's likely that each new revelation will lead to new questions, new hypotheses, and new lines of inquiry, propelling the search for answers forward. The journey toward understanding the universe is an exciting one, full of potential and uncertainty. As we inch closer to the edge of what is knowable, the discoveries we make could forever alter our perception of reality. What we learn about the universe could have profound implications not only for science, but for humanity's place in the cosmos. It's a quest that may one day reshape the way we view existence itself, challenging our most basic assumptions about life, the universe, and everything in it.